When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool.
Portfolio Manager for the Live Events Division at DCD. It is my pleasure to kick off the showcase stage for this year's DCD Asia Pacific with a tech showcase, High Density Cooling for a Sustainable World, with Jan, General Manager Data Center Sales at APAC. Jan, if you would like to join me on the stage.
Thank you, Gabriella. All right, good morning, everybody. So I'm going to be talking about cooling for data centers, especially about liquid cooling, which is a general trend. I'm going to talk about why that is a trend, and also about a real-life case study with immersion liquid cooling for a data center that's been in use for almost a decade now. And so let me just start with a general overview of the trend in data center cooling. So what you see here is a graph of how the market is expected to grow. At the beginning of 2025, there was about 40 gigawatts of data center capacity installed worldwide. And by the end of this year, that is expected to rise up to 50 gigawatts. And by 2030, it's expected to grow up to 100 gigawatts. And according to some more optimistic sources, even up to 200 gigawatts. So most of this growth is going to be driven by AI, as you all may know. So this chart here is split into two colors. The black one is the traditional data storage cloud providers for uploading and downloading and streaming data. And the blue color is really the portion of the AI data center growth, or the AI factories. As you can see, this is really what's going to be driving and doubling the installed data center capacity over the next 5 years. So not only is the installed capacity of data centers going to increase, we also need to talk about density, because AI is a very demanding application for compute. It becomes more efficient when you have more compute in a smaller chip. But the downside of that is that a smaller chip with the higher density compute will generate more heat. And the smaller it gets and the more heat it produces, the more challenging it becomes to cool that chip. And the density of chips is only going to increase, as you can see here on this chart, with the H100, the H200. NVIDIA even has announced, as you may know, a new liquid-cooled rack that goes up to 600 kilowatts, and there's even talks about 1 megawatt per rack. Air is no longer going to be able to cool that. So liquid cooling is no longer a topic about energy saving. It's becoming a necessity for high-density compute. Now, the reason why liquid cooling is so much better than air is quite intuitive. If you compare water with air, and you can use other liquids as well, but let's just think about water for the sake of simplicity, it has a 25 times higher thermal conductivity than air. In fact, air is a thermal insulator, as you all know. So 25 times higher thermal conductivity compounded by the fact that water is also much denser in terms of specific heat capacity. So by volume, 1 liter of water can carry 3,500 times more heat per degree Celsius compared to that same 1 liter of air. So just to put some numbers on why liquid is so much better than air. Now, if we're going to use liquid cooling, there are two schools of thought at the moment. One is cold plate, or also called direct-to-chip cooling, where you have tiny heat exchangers connected with the hot chips on a server, where you have a liquid transferring heat with the chip directly. Whereas the other option is liquid immersion cooling, where you have a tank with dielectric fluid, a fluid that basically does not conduct electricity. It behaves like air from an electrical point of view. And then you just dunk the entire server in that liquid, and then let that liquid take care of the heat transfer. So there are a myriad of in-between solutions between cold plate and immersion cooling. So there is even, direct-to-chip cooling inside an immersion tank. There is spray liquid cooling. So there are some other alterations, but these are really the two main technologies available today. And cold plate is actually the most dominant right now. So I'm now going to move on to make a comparison between these two and talk about the pros and cons. So let's start with cold plates. Here is a simplistic schematic view of what a cold plate cooled data center looks like. So we have servers here that are being connected with a chilled water loop, and then you have a chiller here, and that chiller also exchanges heat with a cooling tower outside of the data center to reject the heat. In addition to that, you also have an air conditioning system that circulates air in the room, because this is one of the things with direct-to-chip cooling. About 70 to 80% of the server heat can be rejected by the fluid, but you still need 20 to 30% of air conditioning for the residual heat that is dissipated by other parts on the server. So the benefits of this system is that it can operate at high fluid temperatures, which can be repurposed for other heat recovery, for example. It has a very small footprint, and it's easy to retrofit because the footprint of a direct-to-chip cooled rack is the same as an air-cooled rack. And it's also a maturing technology. So this is the key reason why this is the dominant liquid-cooled technology today, because the server manufacturers are really embedding this capability within their products. The disadvantages of direct-to-chip cooling is that you now have two separate cooling systems cooling the same IT load. So you have the liquid cooling and you have the air cooling, and they need to work simultaneously. If one fails, the entire system shuts down. So you basically double the risk of failure. Also, direct-to-chip cooling at server level, you have so many tubes and so many connections at each single server that you basically increase the risk of leakage or something going wrong. And finally, that chilled water that runs through the tubes, if it's too cold, the humidity in the air will deposit condensation on those tubes, forming water that, if it comes into contact with the server, will be detrimental to the reliability of your operation. Next, let's talk about immersion cooling. So, as you can already see, this is a more simple design. You have the tanks with servers inside, and they are connected with a water loop system to a cooling tower outside. In most cases, you don't need a chiller, so you can use free cooling. I'll talk about what free cooling is in a minute. So you basically eliminate the need for server fans, the need for air conditioning, and you also protect the servers, because once they are in a dielectric fluid, they are no longer exposed to oxygen, no longer exposed to dust, and you basically increase the lifetime of the servers. So other than that, this is also the more efficient solution in terms of energy consumption compared to direct-to-chip cooling. The only air conditioning that you see here is purely for comfort reasons. So for the operator in the room, it's not mission critical. If there are no people in the room, you can even turn it off. Now let's talk about PUE and TUE, because if we compare air-cooled servers with liquid-cooled servers, and I don't know who's familiar with the concept of PUE, PUE doesn't really do justice to liquid cooling, because PUE is power usage effectiveness, or total facility load divided by IT load. But traditionally for air-cooled data centers, server fans are part of the IT load. And server fans consume already 20% of that IT load. So if for a liquid-cooled data center you remove the servers, you reduce the IT load by 20%. And by doing that, your PUE goes actually up, because you reduce the bottom part of the equation. And so to compare apples with apples, we should be talking about TUE. And so there was an article published in the ASHRAE journal 3 months ago about this. And this is also not a new metric. It's just not as popular as PUE, which says total facility load divided by compute load. So discounting the server fans, giving a more honest depiction of the efficiency of a data center. So let's say, for example, a data center that uses air cooling with server fans that would have a PUE of 1.3. The equivalent TUE would be 1.625 if you use the compute load as a baseline. I'm just mentioning this because we're going to use this later on in the presentation as a basis for comparison. So let's talk a little bit more about heat rejection now. So you have liquid cooling. How are you going to get rid of the heat? And so for that, you can either use free cooling or mechanical cooling. Free cooling is where you have the liquid straight going to a cooling tower or a dry fin heat exchanger. But if the conditions outside are too hot and you cannot reject the heat, then you may need a chiller. So it's basically a refrigerant system that pumps heat from the liquid and then makes it a little hotter to make it easier to reject that same amount of heat through a cooling tower. The downside here is that a chiller consumes a lot of power, maybe up to 10 times more than just a cooling tower. So everybody wants to avoid as much as possible using a chiller. But sometimes it's necessary. Now, in both cases, mechanical cooling or free cooling, you're going to need a cooling tower. And cooling towers work either with evaporation or completely dry. So for evaporative cooling towers, which are on the right of the graph here, you consume a lot of water, you evaporate. The same process as for humans, as when we sweat, we cool ourselves off using water. And that's a very efficient way of cooling. If you have to cool without water, you'll be using dry coolers on this side of the spectrum, then you will consume a lot more fan power to reject the same amount of heat. So diving a little closer into this, or deeper into this, a dry cooler follows the dry bulb air temperature and also has a higher approach temperature because you have a dry contact heat exchange process. And as mentioned earlier, air is actually a thermal insulator, so you will never be able to reach the dry bulb air temperature completely. The best you can do is get maybe 7 degrees Celsius to it, but not more than that. When you talk about evaporative cooling, you follow the wet bulb air temperature, which is 10 or 15 degrees below the dry bulb air temperature. And on top of that, you also have a much better approach temperature because you have a wet contact heat transfer, which is, water is a better thermal conductor than air. If you don't have water available to go for evaporative cooling, you don't necessarily have to go for 100% dry cooling. There are also hybrid cooling technologies, including the dry plus wet contact cooling tower on the left here. And then we also have an adiabatic cooling tower, which is on the inside a dry heat exchanger with wet pre-cooling pads. So both these options, they can help you to reduce energy consumption using whatever water you have available, and even if it's not enough, you can just at least work with whatever you have. So now I'm going to move on to the case study that uses liquid immersion cooling. So this particular site is based in Texas, in Houston, and has 4 megawatts of installed compute capacity. It is 100% immersion cooling. It is 100% free cooling, so it does not use mechanical cooling at all, even during the hottest time of the year. And so it uses evaporative cooling. Inside this data center, there is a provision for 800 tanks. There's already 400 installed, and 300 of those 400 are in use. This is a picture of what the data center looks like inside. There's actually even more tanks than what you can see here within this picture. And so what's inside the tanks is a mix of different servers. We've got the Intel Knights, the Intel Sapphire, and the AMD Genoa, and a few others, all with a combined capacity of 4.7 megawatts if we would leave the fans on. But the fans have been removed, and just by that, we removed 20% from the power consumption right off the bat. So we reduce from 4.7 to 3.76 megawatt just from going from air-cooled to liquid-cooled at the IT level. Inside the tank, we have those servers, and we can talk more about it in detail at our booth here whenever you have more questions. But basically, you have servers racked up next to each other in the tank, and then there is a heat exchanger also in the tank that has integrated pumps circulating the dielectric fluid over the servers. And that dielectric fluid does not leave the tank. It just circulates round and round, while inside the heat exchanger, through the tubes, you have the cold water coming in, absorbing the heat, and then coming out warm. And so that warm water then goes to a cooling tower outside. So at the tank level, the recirculation pump for the dielectric fluid consumes 0.65 kilowatts, or about 5.2% of the compute load that it's handling within the tank. So the compute load per tank is about 12.4 kilowatts. What else do we have here in the data center? We have the air conditioning, just for comfort cooling, as mentioned before. So this is not mission critical. This is purely for the people in the room to feel comfortable. Those air conditioning units, they consume about 20 kilowatts altogether, which is about 0.5% of the compute load. Finally, outside the data center, we have cooling towers and pumps to circulate the cooling water to each of the tanks. 6 evaporative cooling towers and 5 pumps, totaling 296 kilowatt of power consumption. And relative to the compute load, we're talking basically about just under 8%. And so now let's add all of that up and compare that to a typical air-cooled data center that uses servers with fans and an air conditioning system and air-cooled chillers on the outside to reject the heat. If we compare those two, on the left here, we have the traditional air-cooled data center. And so this is the compute load. Here you have the server fan power consumption. This is the air conditioning inside the room. This is the power consumption of the air-cooled chillers outside. And this is the power consumption of the chilled water loop to bring the cool water to the air conditioning inside. On the right-hand side, we have the figures that I just presented for the case study in Houston. So we have one as a compute base load, and relative to that, we have only a little bit of power for the pumps to recirculate inside the tank the dielectric fluid. Then we have this little sliver here of green for the comfort cooling inside the room, and then the gray and the blue here is for the pumps and the cooling towers outside. If you look at this and you compare, you see that the total overhead power consumption of the immersion cooling data center is consuming almost less than half of what just the server fans would consume in an air-cooled data center. And if you look at it in totality, it's about 30% difference at an overall power consumption for the data center. If you look at just the overhead load, it's about 80% less. And so there are basically 3 things that bring us to these energy savings. The fact that we went from air to liquid cooling, the fact that we went from mechanical to free cooling, so we cut out the chillers, and the fact that we went from dry cooling to evaporative cooling. So before I finish, I just want to talk a little bit about BAC. So the immersion cooling tanks and the heat rejection equipment that I talked about is something that we've been doing for 80 years. And so even though we are based or headquartered in Baltimore in the US, we have 12 factories around the world, and especially in Asia Pacific. I can tell you that we have a factory in Australia, one in Japan, Korea, and China. We also have test facilities, and we also have immersion cooling deployments here. So whoever is interested to visit one of those immersion cooling data centers, please feel free to contact us. We'll be happy to organize either a virtual or a real-life tour visit. All right? So with that, I conclude my presentation. and open up for any questions.
Thank you very much. Hi. Can you? Oh, God, that's very loud. Sorry about that. Yes, thank you so much, Jan. So, questions. Before I ask a couple of questions I have prepared, are there any questions from the audience? Because we've got a few minutes. The gentleman here. Sorry, I'm going to hand you my microphone.
Hi there, Jan. Thanks for the presentation. I want to ask about the corrosion factor of the immersion fluid. Uh, does it, yeah, what's the shelf life on these servers that are immersion cooled? Because it's, we have a lot of savings on the TUE portion, but I also want to know how long will our servers last? Yeah.
Okay. So the case study that I just showed you is almost 10 years old, and we have not had to replace the fluid there even once. Now, not every fluid is the same. There are maybe up to 20 different dielectric fluid suppliers in the market, and they all focus on different things like biodegradability or flashpoint or thermal conductivity or viscosity, which also has an impact on the pump power required. A biodegradable fluid is good for the environment, but may need to be replaced every 5 years. One that is a synthetic mineral oil will have a longer lifetime. So it really depends.
Great. Sorry, he won't be able to hear you.
Sorry. Yeah. So in other words, for BAC products, you have a proven test case that it lasts for 10 years plus, which is quite good.
To be honest, 8 years.
Okay.
Yeah, up and running. And
Nice.
happy to invite you for a visit if you're interested.
Definitely, definitely. I'll definitely visit the booth later.
Yep.
Sorry. Any other questions from the audience before I ask a couple? We have about 3 minutes, so if not, cool. Jan, so do you need a specific type of server for immersion cooling, or can you use any model?
You can use any type of server. You can either use one that is made for immersion cooling, or you can convert to immersion ready yourself. If you don't want to do it yourself, there are companies who do that. And there's basically only 3 steps that need to be taken. Step number 1 is to remove the server fans. Step number 2 is to reprogram the BIOS so that the server can operate while ignoring the fault signal from a server fan that is no longer there. And number 3 is to remove the heat sinks from the chips, remove all the thermal paste so that the chip casing can directly contact the dielectric fluid.
Great. And what happens with the server warranty when it is converted from air-cooled to liquid immersion-cooled?
So the warranty is either provided directly by the server OEM when it is issued by them. If an old server or an air-cooled server is converted to immersion ready, the companies who do that, they also take on the warranty on themselves. So if anybody's interested to know who those companies are, happy to share the contact details. And in fact, as I mentioned, the warranty of the server becomes less risky when you put it in immersion fluid because you protect the server. The dielectric fluid acts as a coating to avoid direct exposure to oxygen or dust. So we see from the deployments over 8 years that the fault rate of servers is actually lower than it would be in air-cooled deployment.
Great. Any final questions from the audience before I wrap up? No? Well, thank you so much for your time this morning, Jan. And obviously, the BAC team are on our show floor, so please go and visit them if you do have any other questions. But another round of applause, please, for Jan. Thank you very much.
Everyone.
We keep these on mute in between sessions. So whenever anyone comes off the stage, we mute these for now. Everyone, and welcome back to the showcase stage. Moving on to our next presentation of the morning. DCD Tech Showcase, integrating liquid and air cooling solutions with XCool. It is my pleasure to welcome our next speaker, John Pettit, CEO of XCool. And John, I will leave it with you.
Thanks, Gabriel. Everyone hear me okay? Yep, all good. Excellent. So, welcome everyone. Thank you for joining. Very quickly, I'll give you a bit of a background about XCool. So my name's John Pettit. I'm the CEO of the XCool group of companies. So we've been around since 2010, and we are dedicated purely to data center cooling. We've been delivering, developing, manufacturing, innovating all types of data center cooling for the last 15 years. In fact, for the last, up until about 2020, we focused mostly on indirect active cooling, as it was and still remains one of the most efficient ways of cooling data centers. But I think we realized come 2020, 2021, just after COVID, that the emergence of AI, the emergence of HPC computing, it needed a different approach to the market. And the speed and scale of what was being built had a different, we had a different approach. So we are currently all around the world. So I'm headquartered out the UK. So I have a factory in Birmingham. We've got about 250 people. We manufacture in about 180,000 square foot of manufacturing. We've got offices in North America, in Atlanta. We're in Germany. We've just incorporated into Singapore, and we've just incorporated into Malaysia. We see this region specifically as one of the higher growth regions for the data center market. Very different to maybe 5 years ago, where it was very much a very slow market, but we've seen so much progress and so much development in the last 5 years that we are significantly investing into the region. So we now have a team out of Malaysia that's looking after some sites that we've delivered into Malaysia and Singapore. Potentially, we're going to be opening very shortly into Australia, Japan, and Norway, which is probably of no concern to anyone here. But we're going to be up in Norway because it's incredibly cold up there, and a lot of the equipment that we do works exceptionally well in them kind of regions. A lot of our clients are global clients, and it means that they're building everywhere. So we need to be where they are, and that's the way that we go to business at the moment. So on to today. What are we talking about today? So we're really talking about probably what everyone else has mentioned in their presentation, which is around liquid and air cooling. So I mentioned earlier that up until about 2020, 2021, we were mostly focused on air-cooled solutions. And we were really good at it. You know, we probably supplied more indirect active cooling solutions than anyone else around the world. And we're probably most well known for that, and probably our market leaders. But we've realized that we now need to include liquid cooling. And these two things are not separate. You know, you shouldn't have to be in a situation with a client where he's having to decide, are we going down air cooling or are we going down a liquid cooling route? So the way that we've approached it is probably a little bit different to everyone else. It's, you know, our family of products, our family of solutions that we have together is all about integrating and working as a hybrid solution. So outside of kind of the hardware, if you like, being chillers that we produce or our CDUs that we produce and our indirect active coolers, a big part of it is how do you get all this to work together? And this is kind of the key to it. You know, there's a lot of speak at the moment, about 80% on liquid and 20% on the air, which is obviously the utopia of where we all want to get to. But on day one, what we're finding is that's not actually the case. We're finding that you are getting into a lot of situations where you need to look at things such as there's often a lot of legacy equipment left in data centers, so it's not all AI. So a lot of that has to be air cooled as well. And how do you get the air cooling and CDUs or fan walls or even rear door heat exchangers to all work together in a way that in the most efficient method? So the way we approach this is we have a common controls platform that works all across all of our products, all of our solutions. We have a whole software team that works specifically with clients to go through it. You'll see on the screen behind me is our total portfolio of products and solutions that we go through. Obviously, the flavor of the day, I think, for everyone is CDUs. We have we've probably got about 12 different CDUs at the moment. I think it's still a bit of the Wild West out there on designs of CDUs. So we've got everything. We've got tall ones, short ones, things that look like chest freezers. We've got naked ones. We've got no panels on. We've got ones that are built onto skids that get lifted. And I think it's going to remain this way for the next 2 to 3 years until it's really stabilized in what the market should look like. I think originally people wanted to think that they would look like racks, but the reality is it makes far more sense if these actually go into the mechanical corridor themselves. And there you have a lot more access to them and lots more maintenance. And most importantly, you're not taking up space from within the white space. You know, that wants to be used for the racks. That's where you want to have your chips and your processing, because ultimately that's what earns you the money, right? It's the money, it's the process that happens inside data centers. So we have a full range of suites that go into there. So we have now screw and scroll compressors, CDUs, as I said. We have a big range of indirect adiabatic coolers or evaporative coolers that we've redeveloped over the years. Precision cooling walls or fan stacks, if you like, and a completely dry solution. But we're much more than just a bunch of products. We're much more than just a bunch of solutions. For us, it's about how do we integrate this into a data center. And I think that's probably the million-dollar question for a lot of people here at the show today and within the industry, is in this uncertain times when you're not quite sure what the load's going to be, when people like NVIDIA are changing the loading of their chips quicker than you can actually even build the equipment, how do you future-proof your equipment as you go forward? So we work very closely with people like NVIDIA and other chip manufacturers to come up and get to a point where you're designing data centers and you're putting in equipment that is not going to be obsolete within a couple of years. You want to have a common platform that you can continuously add to, and you can change your mixture of air and liquid together, whilst maintaining obviously your very close approach temperatures on your CDU, obviously managing your air side. You know, we are still doing a lot of data centers that are half air, that's got legacy equipment in, and we've also got a lot of equipment, a lot of data centers that have that are now liquid cooled with CDUs on the side as well. So we are specifically looking at hot and humid environments, you know, for the equipment out in Asia Pacific. Here we're just showing some animations of chillers on a data center that's feeding either firewalls or fan stacks, should I say, and CDUs. But what we're finding here is we're also going to be introducing a range of dry air coolers as well. What I really like about this region is the innovation that takes place, is the willingness to push the boundaries, the willingness to increase the temperatures, which eradicates or certainly minimizes the need for mechanical cooling within chillers. You can reduce the size of your chillers, reduce the size of the amount of power that you consume, you know, for that region. So we are looking at probably two types of approach into the market. We've got the North America market that is actually, if anything, is reducing the temperatures that it wants into the space. And we've got the Asia Pacific market, which I feel is a much more forward-thinking side, which is increasing the temperatures. And I think we'll all agree for the sustainability side of this, we want to be pushing forward with the sustainability message of to reduce power into the data centers. But the key item is to be able to design a system that you don't know what's coming down the line. We know that the likes of NVIDIA are going to be launching much higher density racks. So you don't want to be designing and building a data center now that in 3 years becomes obsolete. So a lot of what we do, a lot of the equipment we design and innovate and install into data centers is around allowing that to be grown on, build as you grow type design. And we're very successful at that as a design, working very closely one-to-one with clients, with end users and operators in that design. We also work very closely with equipment manufacturers, chip manufacturers as well, to make sure that we're hitting all the right points as we go forward. The other point I think it's important to come up with, to mention here, is about how quickly the market moves. Typically, again, you go back a few years, a data center might take 2-3 years to build. We're now seeing from out the ground data centers being built in 12 to 18 months. Now that puts a huge pressure onto infrastructure suppliers, vendors. So again, it's about how do we streamline our manufacturing process? Yeah, and again, this is about relationships, our speed of deployment, but mostly kind of looking at things like long-term master purchase agreements with clients to make sure that we know what's coming up, because we do the manufacturing, but then we still got to buy things like our pumps, we've got to buy our heat exchangers. So we need to give all of our supply chain a forward forecast of what's coming down the road. And I think, again, it's a sign of how forward-thinking the data center industry is that out of all the industries that you could work in, I think data centers appreciate how important that relationship is. And there's a lot more partnerships, should we say, going forward than there is straight out vendor suppliers, which I think is where everyone wants to get to in terms of a manufacturer, especially, look at myself as a manufacturer. I've got, excuse me, with 250 people in the factory running, 7 days a week. We need to know what's coming on in 6 months. We need to know what's coming on in a year's time. So I'd like to say we're lucky enough that we've got probably 8 or 9 very close relationships with major clients that enable us to be able to forecast it as we go forward, which helps us ultimately with speed of deployment. So we're able to build, we're able to stock, and then we're able to deliver as and when required. So one of the methods we use for this is, I'll go back to the CDU design, because that's probably the most common one that we're doing at the moment. In my naivety, a couple of years ago, I thought I'd end up with 2 CDU lines, a small one and a big one, effectively. We've ended up now with 6 or 7 lines of CDU manufacturing for specific clients. So client A has his own specific CDU, client B, she has her one, client C, client D, and then we just build as we go forward with them. So I think at the moment we're still going through time where CDU design is being refreshed very, very frequently for us, and it's important that that we stay ahead of the game, and it's important that the market stays ahead of the game as well, because I think we'll find as we go forward that there will be better ways of doing what we do today. And I think that's important for us as an industry to consider as well. Is that as much as we like to think we've got all the answers now, we haven't. And the industry moves so quickly, and everyone needs to be on board as we go forward. Everyone from the vendors to the owners, operators, to the actual equipment manufacturers themselves. So vendor collaboration, I think, as I mentioned, is hugely important for us. Ensuring that we hit all the standards and specifications that are coming out now, be it ASHRAE or be it other organisations that are launching their specifications now. I know the NVIDIA are coming out with their set of standard specifications, but then what I'm also finding is the major colo operators have also got their own design, but when it comes to it. So vendor collaboration for us is absolutely key. And it's a completely different model to what the market was 5 years ago, or even 10 years ago. I've been doing this a long time. I've been in the industry 20 years, and it's now a completely different market, I think, to where we were 20 years ago in this, for sure. So we do try and work through our clients with a very strict protocol of our program as we go through with the designs for them. The way we typically work is when a client comes to us with a new CDU design, we will build that design. We will typically do it at our cost on the basis that we will build it. We'll put it into our test chamber. I've got 2 test chambers in the UK to test it to the performance levels that's required, at which point orders are placed, stock is built, and then we're happy to hold it here We've got places in Malaysia to hold it. I've got places in the UK. I've got places in the US to hold it. And this model kind of works at the moment with everyone as we go forward. So we're keen to continue with this model as we go forward. We don't have all the answers, but I'd like to think we're getting close to being able to help the industry in a point where you can integrate your CDUs and your air systems together. So it's on a almost holistic approach, on a hybrid approach. So the design and the control strategy works in a way that that can suit many different environments within the space. So that's probably close to the end of my presentation. You know, it was more about XCool and what we're doing and our movement into the Asia Pacific market. We've kind of been active here for about 2.5 years now, and we're going to be moving quite quickly now. We're looking at bit larger premises in Malaysia, potentially production and manufacturing processes here, but also designing specifically for this region. So thank you everyone for listening. Happy to take any questions. I think I've been a bit quicker than I expected to be.
Thank you so much, John. Questions? Anyone from the audience before I kick off with mine? But I like to give the audience a chance. No? Okay. Oh, we do have one in the front. Sorry, I'm just going to have to hand this over to you.
Hi, John.
Hi.
Rowan Peck.
Hi, Rowan.
From Canberra in Australia.
Yeah.
So question, and
Yes,
you might
sir.
not be able to answer this. What do I do for a dry cooler if I'm looking at 38 to 40 dry bulb and about 29 wet bulb temperatures?
Yeah,
Which
so,
is a typical
yeah,
tropical climate in this
absolutely.
region.
So the ones that we've looked at, it's a great question, Rowan, because if I look at the two sides of the world, so yeah, we've just come back from looking at some projects in the US, and they are driving temperatures down. So yeah, we've got no chance of using dry coolers. It's chillers all the way in terms of the temperature. But over in the Asia side, where we've seen there is a combination of both dry air coolers and chiller backups on that same circuit feeding into the CDUs. So that's what I think we'll see, and I think we'll see that as it goes more. So dry air coolers to do it as much as it can, but with the backup of chilled water to provide should the temperatures get to the point that the dry air coolers can't provide it, the required temperatures into the CDU. Does that make sense? Yeah. Thanks, Ron.
Any other questions from the audience? Yep. Oh, sorry, there's one here, and then if you pass it to the gentleman.
Hi.
Hi.
Do you plan to provide service in Australia also?
Yes, we do provide. Yes. So our MO. So you've seen us. We're not the biggest company in the world. We are. We're very innovative, but the way that we go to market is when we get to a point where we know we're going to have critical mass of equipment in a region, we will open and we will staff it out. So Malaysia was a great example for us. I've got probably close to 250 units in and around the Johor area now. That's enough for me to open an office. I've got a dozen or so techies out there now working permanently. We're actually looking at a couple of projects in and around Australia that we're thinking, actually, if any one of these comes off, it's big enough for me to open an office and put half a dozen techies in there. It's the same method we use with North America. It's the same method I'm using with the Nordics. It's chicken and egg, right? Do you open and then go, oh, actually, we haven't got any work, or do we wait for the work and then we open? So that's our MO. But Australia for us at the moment is really high. So Australia, Malaysia, Indonesia, and Thailand, they are my 4 targets for this region.
Thank you.
Thank you.
Hi, John.
Hi, how you doing?
Not too bad. And funny you should mention Malaysia. So I'm from Basis Bay, and we are a Malaysian data center company. So definitely we should connect.
Absolutely.
Where's your office?
So we're funny enough. I head from here tonight into Kuala Lumpur because I've got to sign the final bit of paperwork. But it's going to be just out, so we're going to have a small office in KL,
Nice.
but my bigger office is just outside Johor.
I see.
Yeah.
Well, I mean, we're practically neighbors, so
Perfect. Yeah.
we'll connect.
That'd be amazing. Yeah, we're just over there on number 3, so please come and see us. That'd be amazing.
Thank you.
Great. Any other questions from the audience? I have a couple, and I know we've got about 5 minutes left. So if we don't, I can ask a few of my own. Nope. Okay. So,
Yep.
John, why should operators consider integrating both air and liquid cooling instead of just choosing one?
So what we're finding at the moment is there's still a lot of legacy equipment out there, and where some data center operators are not willing to go all liquid, so they're still holding a lot, maybe traditional cloud storage or something inside of the white space that needs air cooling. Air cooling, especially something like indirect adaptive cooling, adiabatic cooling, there is no more efficient way of cooling down a data center. So if you can possibly avoid using chillers and get away with upping your air portion of the cooling, that's a much more efficient way of going about trying to cool down your data center.
Great. And what are the biggest technical challenges in integrating the two systems?
The biggest one is getting them to talk to each other in a way that can be managed. So again, I'll go back to probably how I started this, where people are ideally you want an 80-20% split, but the reality is on day one that might not actually be what it looks like. It's might be a closer to 50-50 split or a 60-40 split. But also fundamentally, you've got to think about these two. The two systems operate very, very differently. AI type data centers or racking works instantaneously. When we test, we're testing 10 to 100% ramp up within less than 10 seconds. So in our test facility, we're having to show performance of the CDU with an instantaneous load. Whereas a more air-based load generally takes a little bit of time to get up. So they're very different. So that's a challenge. So keeping all on the same platform is a real help.
How does the CDU help with hybrid cooling?
So the CDU helps with hybrid cooling in similar to what we're talking about here about you've got the ability to not specifically run it off chillers. You can also run it off dry air coolers as well, which is a much more efficient way of trying to run down a cooling system, that's for sure.
What are the space and infrastructure impacts of adding liquid cooling to an air-cooled site?
Typically, it's going to be quite. Any retrofit is difficult. I'd much rather add cooling to an air site than air to a cooling site. Put it that way. You will typically have chillers on site, and as long as you don't mix your circuits, you could end up with adding a few more chillers and have some chillers running your fan walls or your rear door heat exchangers, and the others running a CDU system.
I do have one last question, but I want to give the audience one last chance before I wrap this up. So, nope. Okay. So are there any proven examples of hybrid systems already in use?
Yeah, so we've got a few. So we've got one in Europe, and we are just finished delivering one in North America at the moment. Extensive testing was done on the software and the sequence of operations to get the two systems to work together. So we had the client at the factory for several times for days on end, just running through their exact requirements. And believe me, their exact requirements are completely different to the next client's exact requirements. And we'd like to think that there's some kind of standardization, but there's not. We kind of need to get there at the moment. We're really good at being adaptable and flexible. And I think that is what sets someone like Xcore apart from maybe some of the other competition, because we're able to be that flexible.
Oh, question just here at the front.
Yep.
Sorry, we're just getting the microphone to you.
Hi.
Hi.
Thanks for sharing.
That's okay.
I'd like to know for the hybrid system, what tiering of a data center is there?
That was a tier 3. Tier 3, yeah. Everything was run on N+1 apart from the liquid side, which was N+2.
Thank you.
Okay.
Brilliant. I think we're at the end. So thank you once again, John.
Great.
A round of
Thanks very
applause,
much.
please.
Thanks, everyone.
And as he mentioned, Xcore are just over there if you'd like to go and speak to them. Thank you again.
Thanks for listening. Thanks, everyone.
When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool.
Brilliant. Hello, everybody. We're about to kick off our next tech showcase of the day. I'm delighted to welcome to the stage Liam McDermott, who is Sales Development Manager for Data Centers at Grundfos. And we're continuing our cooling theme, if you hadn't noticed. We have quite a few cooling sessions back to back. So if you're into cooling, this is the stage for you this morning. Liam is joining us to share some insights into distributed pumping, which is a paradigm shift towards decentralized pumping. So I'm going to hand over to him. And here is your microphone. Thank you very much.
Thank you, Rebecca. Good. Rebecca, can you hear me?
I can.
Yeah. Okay, everything's working. Good morning, everybody. As Rebecca introduced me, my name is Liam. I'm part of the global sales development team in Grundfos, and I'm going to introduce you to distributed pumping. I'll tell you first a little bit about Grundfos, what we do and who we are, and if I can just get the, there we go. Yeah, I'll tell you a little bit about Grundfos, our sustainability goals and what we do with sustainability, distributed pumping, and then I'll share some information on a case study with you. So, as you can probably gather, I'm not from around here. I'm from Ireland. I've travelled from Dublin last week or this week to join the event. So, a little bit about Grundfos. We're one of the world's largest pump companies. We're founded in 1945. We're a Danish company. Our headquarters are in Denmark, but we have operations. We've got sales offices, manufacturing, whatever, in over 60 countries. So we've 80 companies in over 60 countries. And We are privately owned. We've got a turnover of about $5 billion, so we're quite a big company. And our promise is to respect, oh, sorry, this is flicking on a little bit too quick. Our promise is to respect, protect, and advance the flow of water. So everything we really do is geared around water, water movement, and how we use water in systems. And as I mentioned, sustainability it's very big for us. We've been working with sustainability back since the beginning of the company. And the areas that we concentrate on are energy savings. So pumps use a lot of energy, and it gives us great opportunity for saving energy if we use them smartly and wisely. The other areas are saving water. Water it's a scarce resource, and yeah, we like to kind of remind people of this, and that we've all got a responsibility when we're using water to use it as efficiently as possible. So once again, by using technology, we can save water. Access to water for people and communities. We work with the Red Cross, we work with the UN, and we work with other agencies to bring water to communities that are struggling with water. And a circular business, circular economy. So we reuse, we recycle, we do whatever we can to make our products as eco-friendly as possible. And we're the first pump company or water solutions company to have our science-based targets approved. You can see here that by 2030, we will reduce scope 1 and 2 by 50%, scope 3 by 25%, and by 2050, we will have reduced all by 90%. They're quite strenuous targets, but we're working towards it. We're producing our reports to show where we are on this journey, and we firmly believe we will make it. And we believe that by doing this and by working with water saving and with energy saving, we can cool data centers without having too big an impact on the planet. So if we look at distributed pumping, and I'm not going to go into all of this here, like we all know that the way we're using data, the way we're operating data centers, our energy consumption is just increasing all the time. It's going to continue to do so. So it's important that we use clever design, that we use the latest technologies in how we move water around a data center, or any other buildings for that matter, to cool, to heat, to do whatever we have to do. So if we look at distributed pumping and how it works, distributed pumping, as Rebecca said, is a paradigm shift. It's a new way of moving water around a data center to achieve the cooling that we want to achieve. And basically what we're doing is we're removing unnecessary valves. So we're taking valves out of the system and we're replacing them with smart and efficient pumps. And we're also balancing the flow between the primary side and the secondary side. And by doing that, we make the system much, much more efficient. And I'm going to touch upon how we do this and the methodology. So the benefits of distributed pumping. We reduce the energy consumption in the pump systems. And as mentioned earlier on, pump systems consume huge, huge amounts of energy. And there are lots of them in cooling systems and other systems as well. So if we can look at how we manage them, how we operate them, there are great opportunities there for us to save energy. We balance the systems, so we balance the primary and the secondary systems. Once again, there's a lot of efficiency to be gained by doing this. It facilitates modular design. So by using distributed pumping and using pumps out in the field at the point of use, we can change the system without having to rebalance all the time, redesign all the time. So it makes it very, very adaptable. And we manage to control the delta T on the system. Low delta T syndrome, we would all come across this in chilled water systems. And distributed pumping focuses very heavily on making sure that we get the delta T exactly as we want it. So we're delivering the right amount of cooling into the system, not too much, not too little, just the right amount. And once again, we have big energy savings by doing that. some of the additional advancements. The design process we simplify because we decouple the system, the primary and the secondary systems. It makes design and working out the index run and all this kind of stuff, it makes that much more simple. It takes the complexity out of it. Modular design, as I mentioned, because we have a pump at each of the circuits, it means that we can switch on or switch off circuits. We can add circuits. If we add a circuit onto the system, we add another pump onto the system. If we take some circuits out of the system, once again, the system will start to realize that and it will rebalance itself because we have sensors which are giving feedback to the pumps and how they operate and how they work. And which is probably a little bit unusual for most of the other systems, we get heavily involved in the design of this system. So we will take a consultant's design, we will put it through our programming, and we will make sure that everything is designed as it should be. So we take a lot of responsibility here, and we pass the documentation back. So if we look at a standard system and how it would normally operate, we've got our chilled water plant down here. We've got our points of use up here. It could be a craw unit, it could be a fan coil, rear door heat exchanger, CDUs, whatever. We're feeding cooling liquid to those. And if we change that to a distributed pumping system, we basically take away the valves and we put pumps in their place. And the pumps are working on sensors and they're giving the exact amount of cooling for the application. So if this is a rear door heat exchanger or whatever, we're measuring what the cooling load is and we're matching the pump to meet that cooling load. And by taking away these valves, we take a lot of the back pressure out of the system. So by doing this, we can reduce the size of the whole pumping equipment because pumps are sized on flow and head. If we reduce either of them, we reduce the size of the pump and the energy consumption. In this case, we need to keep the flow the same, but we can reduce the head, we can reduce the actual pressure that has to be delivered into the system. And by doing that, we automatically reduce the energy consumption. And it makes commissioning very easily. Because the pumps are working off sensor feedbacks, they're speeding up and slowing down according to what is happening in the system in real time. It makes this commissioning very simple. We don't have to throttle valves and manipulate the system in that way. The pumps are self-adjusting and they do it themselves. And it works for most systems. I will say it doesn't work for every single system, but we will check in advance, and if it's not suitable, we go to a different system. So if you look at a variable primary circuit, it's got lower capital cost, it's space saving, and it's got reduced power consumption. But there are some disadvantages as well. The design is complex. Commissioning it can be very difficult, and keeping it commissioned can be difficult as well. And getting this index circuit right and figuring out where the index circuit actually is, and is it always going to be the index circuit, once again can be a little bit difficult. So distributed pumping can deal with that. But if we look at the constant primary and variable secondary circuit, it's designed in a different way. It takes up a little bit more space because you've got more pumping plant. It is easier to commission and it's easier to maintain because you've got your second set of pumps out here, which are looking after the secondary side. But once again, there are some disadvantages, higher capital cost and more space required, which is always at a premium. Both of those systems can be replaced with a distributed pumping system, and it'll look like the same system. We've got our primary and we've got our secondary side out here. And the same advantages accrue then to both systems. So if we look at a conventional system and some of the pains, getting the valve selection and the valve authority correct can be difficult. Commissioning can be difficult, and keeping the system commissioned can be difficult as well. Future expansions, once again, can mean going back and redesigning or changing the system in some way. All of this really is overcome with distributed pumping. And I'll go through it in a little bit of detail now. I like to think about distributed pumping that we separate both systems, primary and secondary, and we treat them individually. And then we link them up again in real time. So if we look at the primary side over here, each of the pumps has a designated load, and that pump only cares about what that load is. So if this is a fan wall, it's speeding up and slowing down to give the right amount of cooling to that fan wall. It doesn't have to worry about anything else. But each of the pumps is designed to take the liquid from the decoupling line back to its own circuit. So if we switch off these two pumps here, this one will work a little bit harder. If we switch them back on, it will back off and they will take up some of the load. So the whole system is automatically readjusting itself all the time to what the actual load is on the secondary side. And the primary side is doing its job as well, and I'll go through that now in 1 second. So by using the decoupling line here, and I'll stress this, we don't want flow in the decoupling line. It's there for a reason. I'll point that out now in 1 second. So the secondary circuit, as I mentioned, is looking after its own load. The pumps have sensors, and they will really adjust, speed up, slow down to give the right amount of cooling to its own load. If we look at the primary side's job is to deliver enough cooling water to keep the secondary side happy. No more, no less. So we have a methodology for doing this. So how we treat the primary side, we use a controller called an MPC controller. This is the common controller that we use in all our booster sets, all our HVAC applications, water applications, or whatever. So it's a standard product that we just put some programming into. And we switch on a chiller, or there's a load called for, our chiller will come on and the pump will come on. The first thing we do is we check to make sure we got the minimum flow on the chiller. We do that by measuring the delta P, the pressure across the chiller. And if it's not reaching the minimum flow, we speed up the pumps to achieve that. Once that happens, we then start looking at the secondary side to see how much cooling has been used out there and to deliver that amount of cooling. The ideal situation, we're delivering enough cooling out to the load to keep it happy. And how we use the primary side overlooking the secondary side is we use temperature sensors. So T1 should equal T2 and T3 should equal T4 in the ideal situation. If that's the way, we have the system completely balanced. So the primary side is generating and delivering enough cooling out to the system to keep the units out here happy. As these units, their load adjusts, the pumps here will see it by the temperature sensors and they will adjust accordingly. And this is all happening in real time. So, in a situation like this, we have balance, we've got the temperatures the same, we don't have flow in the decoupling line. If we start to get imbalance up here, we are under pumping, so we're recirculating water from the hot side, and we will speed up the pumps on the primary side. The opposite happening down here, where we're out of balance on this side, we're recircling from the primary side, and we will slow down the pumps. And this is all happening in real time, and it happens pretty fast as well. I've looked at it, and we've got this in our factory in Singapore, and I think within about 30 seconds or so, we will see this coming back into balance if we manipulate it and take it out of balance. So the sequencing, once again, we start the chillers, and we check the minimum flow. We speed up or slow down the pumps to achieve that minimum flow, and then we're all the time speeding up and slowing down the pumps to meet the load we have on the secondary side. So looking at how it looks on an application side, or at a level down here, we got a coil. We can take signals from the pump itself. We can take signals from sensors, air sensors, water temperature sensors. We could use pressure sensors. We can take a signal from the BMS. It doesn't really matter. The pump will interpret this signal and speed up and slow down to give the right amount of cooling for the application. So in summary, basically, we're balancing the primary and secondary side. We're keeping the delta T as it should be, which leads to big efficiency within the pumping system. The pumps on the secondary side are providing the correct amount of cooling for the application. They're doing this through sensor feedback. We're using a non-return valve over here so that as parts of the system shut down, we're not getting backflow through the system. So once again, we're watching that from an efficiency point of view. And because we're taking out the valves and we're removing a lot of the pressure that's required in the system, we can accrue big energy savings through that. So our energy savings are coming because we've less back pressure on the system, because we are manipulating or speeding up and slowing down the pumps to meet the exact load. And then the primary side is watching what's going on there through the temperature sensors to match that exact load as well. So if anything happens out in the secondary side, it's reflected in the primary side through the primary pumps. And the pumps are just delivering the amount of cooling liquid, cooling fluid that's required. If we overpump, we use more energy. If we pump just the right amount, we use less energy, and energy savings through all of that. And I mentioned the workflow and that we get involved in the actual sizing of this. So when we get a project to look at, we will take the P&IDs, the design file, we will run that through our program and see that the pipe sizing are correct and see that the application, the coils, the chillers, whatever, that everything is of correct size. And we will then put this into a distributed pumping format and give it back to the client and let them have a look at what we've come up with and make sure that they're happy with it and make sure it all makes sense. Quite often we will see areas where we can recommend maybe pipes could be a little bit smaller to get more efficiency out of it, so we can increase efficiency in these ways as well. And as I mentioned, the whole project will be hand back in a design, and it will also include energy recommendations, and we will also look at what it would have been with the energy consumption with a standard system compared to the energy consumption with a distributed pumping system. And as mentioned, we generally see quite big savings. Most of the distributed pumping systems that we have worked on so far, the pump energy will come down by about 40 to 50%. That's the pump energy, what we're using in the pumps. So big systems with a lot of pumps in them, with a lot of flow and head in them, you will see big energy savings. What we struggle to measure in a standard system is the amount of energy we save by balancing the delta T. In our factory in Singapore, we know, because we're doing a lot of measurements there that we wouldn't normally do in a system, we're bringing down the efficiency of the system by 12 to 14%. So if you kind of say 10 to 15% efficiency on the whole chilled water system, plus your energy savings on the pumps, it's quite considerable. And that's by working with the delta T and making sure that we're delivering the right amount of cooling out into the system to be consumed. And the products that we're using in this are our standard products. So for those of you who know a little bit about Grundfos, you probably will recognize some of these products here. They've got built-in variable speed drives. If you go to bigger pumps, we use an external drive, so above 22 kilowatt we use an external drive, but it's the same technology really. And these pumps have energy optimization built into them as standard. We have sensor, that we can use our own sensors or we use external sensors, and the hydraulics obviously are as efficient as we can get them, so they're optimized hydraulics as well. And I think one of the keynotes on this is they're standard products. There's nothing really unique about distributed pumping. It's just the way we pull the products together and use them in a more unique way. So these are off-the-shelf products for most And from a connectivity point of view, they all run on BACnet, Modbus, whatever the standard protocols are. So we just put a card into them, and then we can get all that information back to the BMS system, and people can see exactly what's going on in real time. So our pumps, they have a lot of technology built into them which can help us look at how a system works. And if we have a look at a case study, without going through too much detail on it, but this system here had 10 30 kilowatt pumps M+2. The energy consumption was projected at almost 700,000 kilowatt hours. We replaced the primary pumps with smaller primary pumps, 11 kilowatt, and then we had smaller pumps out on the system as well. And the energy consumption turned out to be just around about 400,000 kilowatts. So it's about 40% energy saving on the pumps themselves. And that's a moderate sized system. If you get into bigger systems, obviously, the energy consumption is going to be larger again. So 300,000 kilowatt hours of saving, which is considerable. I've now come to the end of the presentation. A little bit ahead of time, but can't hear you. So while Rebecca's getting the microphone working, we're going to ask for any questions from the audience. No, still not working.
This.
Yeah, it
Yep.
is now, yeah.
Sorry. Questions, anybody?
Hi, my name is Alex from NTT. Two
Hi, Alex.
questions.
Yeah.
If I have a continuous cooling requirement, where would I put the buffer tank? That's one. Second is, am I saving on pressurization unit if I have a distributed pumping system?
I'll address the second one first. You probably will have a pressurization system in there still. The system, it's only how we distribute the system is good. The hydraulics are going to still need a pressurization system.
Okay.
Where is the buffer going to be?
Yes. Because you have a decoupling line.
We've a decoupling line, yes.
Yeah. So would that be downstream or upstream of the decoupling line?
I'm going to have to think about that one. I'm going to have to think about that, Alex, and I'll come back to you.
Really designing a chill water system for a long time. I have thought about distributed pumping at some point in time.
Yeah.
But I've got that issue of locating a buffer tank. And at some point, I was thinking of oversizing the pipe so that I can make use of the thermal mass.
Yes.
But then again, it may not be that good because of the spaces that I need, the risers, you know. So I think this is an opportunity to know whether distributed pumping system is compatible with this continuous cooling, having a buffer tank with the pumps itself, or without.
I will come back to you on that because I know we are using buffer vessels and buffer tanks on them. I just said, like you said, you've been thinking about distributed pumping or whatever. This has been looked at by ASHRAE 20 odd years ago. People have worked on this.
Yes. Other projects besides data center, yes, I've done a couple of distributed pumping. Yeah.
Very good.
Yeah.
So it's really only been commercialized now.
Right. One more question. Yeah. Now the trend is having an integrated pump on the chillers. Would that be still compatible with the distributed pumping?
Yes, we could integrate that into a distributed pumping system. Now we would have a variable speed drive on those pumps. I know some of the chiller pumps don't have, but we could work it with the integrated pump.
All right, thank you.
Yeah. Thank you, Alex.
Question is around how does this handle failures? So for those individual pumps on the individual loads, if they were to fail, how does the system handle that failure?
once again, it depends on the design of the system. So if you saw the application here, it's N+2. So these are fan walls and crawl units, and each fan wall, it's in an N+2 configuration. So if a fan wall goes down, then the other one steps in. So in that way, we have redundancy. In other situations, we can either use twin pumps or 2 pumps on a circuit, or else we're looking hydraulically how we can, if you had a circuit with 8 or 10, or a line with 8 or 10 branches off to CDUs or something like that. So each CDU would have its own dedicated pump to it, and then we would have a spare pump on the line that comes in if there is a failure of one of these pumps, and it's hydraulically, with valve switching and whatever. We've developed something which is a soft PLC that we can put into these pumps as well, and these pumps, that can be programmed to do different actions. So we're looking technically at using that application, that if there's a failure of one of the pumps, the pump actually opens a valve, or one of the pumps on the system opens a valve to allow this other pump, which is a spare pump on the line. We would designate that pump to cover 1 or 2 loads or whatever, and talk to the client about how much redundancy they need in that case. So it's doable. It's just something, a little bit of hydraulics needs to be done on it.
If there's no other questions, I have one more.
Yeah.
For the decoupling line, what are the pros and cons of using the temperature sensors versus a flow meter to determine if there's backflow through that?
The temperature sensors are going to give us the exact delta T, and we're going to speed up and slow down the pumps on that. If we have flow we need flow into the decoupling line if the chiller load is greater, if the minimum flow in the chiller is greater than the load out of the system, so we will have flow in the decoupling line in that situation. If we get beyond that and the flow out of the secondary side is greater than the minimum flow on the chiller, then we're using the temperature sensors to make sure that we're only putting enough fluid out into the system to keep the secondary side with enough flow, if that makes sense. So if we're doing that, we're not going to get the flow back. If we are getting the flow back, we're going to speed up and slow down the primary pumps to avoid that flow into the decoupling line. Does that answer?
Yeah, it was more around why not use a flow meter? Why use the temperature sensors?
I think probably from a capital cost point of view, the temperature sensors are the way to do it. Also, if we're working on delta T rather than actual T, so we're only looking at the temperature difference, the temperature sensors give us that flexibility where the flow meter, I'm not sure if it would give us that flexibility. So we can play around with the delta T, and we can program the MPC controller to be keeping an eye on the delta T rather than the temperatures themselves.
Thank you. We're actually out of time now. So if you do have any other questions for Liam, please do visit him at their stand. It's just over there, number 10.
Yeah.
And that just leaves me to say a big thank you to Liam for joining us today and for sharing those insights.
Okay. Thank you, everybody, and thank you for your questions. And as Rebecca said, we're over on stand 10 if anybody wants to go over and go through it in a little bit more detail.
Definitely.
Thanks all.
Thanks so much.
Our next session is going to be with Operate and Andrew Kernebone on Smarter Edge, Smaller Footprints. Andrew is going to be with you for the next 25 minutes. Andrew, if you'd like to come on stage for your presentation, and over to you, and then I'll come back for a little Q&A at the end.
Thanks very much, Audrey. Hi, everyone. For those of you in the audience here and those of you walking around with headphones on, good to see you and good to be with you for about half an hour or so. I've got, I guess, a question for you. If I was to say to you, I could save you around 40% of your upfront costs on an edge build, if I could save you around 40% of your ongoing OpEx costs on an edge build, and if I could deliver all of that for you something like 12 times faster for an edge build, what would you say? You'd probably say, you're bonkers, you're crazy, can't do that. Can't do all those three things. Well, today I'm going to share a case study with you where we did exactly that for a customer with an edge build, a specific edge build. It's an example where we will manage to deliver those savings, but I think the broader message is to look at the application of that approach across different verticals and see how we can build smarter with a smaller footprint at the edge. So my name's Andrew Kernebone, as already introduced. I'm the Tech Director for Operate Global in Asia. A couple of trends that are driving, I guess, the push back to the edge that we see, and I don't think any of these are going to be news to any of you, but one of the challenges we see at the edge is around the suitability of edge locations. We see organizations trying to deploy an edge site where it may be an existing facility that is simply not up to scratch. It may have been built or developed 10 years ago, 15 years ago, and is being asked to support an edge deployment that's not suitable anymore. We see, and if you've listened to any of the panel discussions and other presentations today, you would certainly see that efficiency, energy efficiency and sustainability are two key things at the edge. Increasingly, we're being asked to deploy higher kilowatt numbers at our edge locations and at all locations, but at the edge that can pose some significant problems, and that's kind of tied back to the first issue with the location constraints, where we may have a site that has a particular sizing, and now we're now being asked to go from, say, 5 kilowatts a rack up to 10 kilowatts a rack. To do that requires a significant upgrade. So looking at how we deploy that edge in a smarter way or in a different way can save us not only money, but also save us ongoing and make us more efficient. And then I guess one of the big trends for why we're doing this in the first place, why do we have this constant pendulum swing of centralize everything and decentralize everything, or then land somewhere in the middle? I think for those of you who've been around long enough, and I was chatting to one of our colleagues last night about that computing industry as an example, where if you've been around long enough, and I dropped the name VAX, and not talking about the last few years, but talking about the computer system from many years ago, a very centralized system. Not long after that, we went from that sort of thin client centralized approach out to a thick client, very decentralized approach. We've seen a similar trend in the data center world where we had a very edge-focused approach. We've pushed a lot of things into the cloud. And what we're seeing is organizations trying to figure out now what's right for them. So there's often a hybrid approach, and often the approach that's requiring an edge compute at the edge is because of latency reasons and bandwidth reasons. So some obvious examples there are telco, where if you're deploying a multi-service edge, you obviously need to have certain applications deployed out at the edge so that the latency and the user experience, the latency is low enough that the user experience is good, that we get the experience that we're expecting. Or it could be a bandwidth requirement where we're bandwidth constrained between the location we're deploying at the edge and the core location where we may want to deploy, but simply having the bandwidth requirements. So think of healthcare, for example, where we're doing medical imaging, trying to send all of that MRI data or CAT scan data back to a core location and back again is going to cause an issue from a user experience perspective and from a health outcome perspective. So what does the smarter edge look like? I've got a couple of examples, a couple of our examples here to give you a sense that the case study that I'm going to talk about today is just an example. It's an example that I have specific numbers for because we built it. But here are some other things that we've built and designed for organizations that give you a sense of how you can look at the edge a little differently. So if you start at the top left, For those of you who were here last year, you would recognize this image. This is our trackside micro data center for Red Bull Racing. We deliver trackside data centers for a couple of the Formula One teams. In fact, we provide services to 8 of the Formula One teams. They've got a very specific requirement. They deploy an edge, a critical piece of infrastructure at the edge in pit lane every race. For them, it's the glue that sits between the telemetry and the control on the car and the teams that are monitoring the car and the teams back in headquarters in the UK who are pushing changes to the car real time during the race. The challenge they had was trying to deploy not super high performance, but fairly high performance compute out at the edge in a location that was very unfriendly for IT equipment. So they were seeing equipment failures. We worked with them to develop an edge that was transportable, easy to deploy. They have a couple of sets of these that they carry to the different races around the world, but it protects the equipment in its own ecosystem. It has its own cooling, power, redundancy built into that edge. Top right, you see a prefabricated solution. This is a design that we've deployed for a number of government departments, a number of different sorts of organisations, but this particular design was done for a national police service where, again, they're looking to deploy an edge. The options were to build a building for their data centre or to convert part of a building that was in use already. Instead, what we did was work with them to come up with a design that could be developed in the factory, so prefabricated, fitted out, carried to site and installed outside their existing building. And that approach worked so well, we went on to work with a couple of other departments in that country to deploy the same solution. Bottom right, very simple deployment, you might think, but an application for an edge within an edge. This was a university deployment where they were looking to deploy a HPC cluster inside an existing white space where the white space couldn't accommodate the kilowatts required, the density required in the edge racks. So what we worked with them on was a solution that would be self-contained, that would include its own air cooling and its own liquid cooling for the direct-to-chip liquid cooling, and could be deployed inside their existing white space, but be heat neutral to this space. So they didn't need to upgrade their air conditioning or any of the other services in the data center. They were able to install this and run it as a separate unit. And then at kind of the other end of the scale of the things we've been looking at is another prefabricated solution to design for the telco world. So here's an example where the edge location, an existing telco location has run out of space. They have power available. They no longer have any space, physical space inside their building. They're completely maxed out. They don't have enough land to build a new building, but they do have some land near the data center. So this design allows them to deploy a prefabricated edge inside the envelope of land they have available with a fully redundant, essentially a modular approach that gets them from 50 racks day one up to a couple of hundred racks on day 4, I think it was. It was a 4-phase project. I guess the key thing that the edge looks a little different to everyone. So if I'm to loosely define what the edge what the edge is, really it's my equipment at my location. Whether I'm an enterprise deploying my own kit or whether I'm a telco deploying my own data center, it's not the cloud as such, it's my own location at the edge. So let's jump into my real world example. This case study is taken from a customer, a client of ours. They are an international tire manufacturer headquartered in Italy. Probably narrows it down a little bit. There's only a couple of very well-known Italian tire manufacturers. They were relocating due to expansion, their headquarters in their UK office. So they to step back, they had taken on a lease, a 5-year lease in a building, taking 3 floors in a new building. As part of the designs of that edge location, of that new headquarters location, the architects specified in a server room. Pretty common requirement. They had a need for an N+1. They had a bit of equipment that needed to go in there, as we'll walk through in a minute. And so they came to operate for help with building that server room. So the requirement for the server room, 40 kilowatts of IT load, spread across 5 racks. So a fairly typical kind of edge deployment, 8 kilowatts a rack. They'd specified about 45 square meters of space, so a 9 by 5 floor plan. That was enough space for them to accommodate the racks, a pair of N+1 40 kilowatt coolers, a pair of N+1 40 kilowatt UPSs, built with a raised floor, pretty standard build, looks very, very familiar to anyone who's ever been inside any sort of edge data center. Our team that went to site and did the inspection and talked to the client realized very quickly that what they're asking for, while it's very common and that's why how we normally build the edge, could be done in a different way, could actually save them quite a bit of space, quite a bit of money up front, and some ongoing costs. So what we did was work with them on an alternate design. So we still gave them the design. We spec'd it out. We would have happily built that for them if that's the way they decided to go. But what we designed for them instead is an alternate solution. We came up with a smarter way to build that edge site for them. And we used, in this case, a micro data center approach. So as you look down the two lists, if you can read that, if the text isn't too small, you can see that they're actually pretty similar in terms of what we're delivering. It's 40 kilowatts of edge IT load. That hasn't changed. They still have the same requirement. Real estate, a couple of significant changes. We're able to deploy that solution in about 18 meters squared. That's going up one rack from 5 to 6, and leaving just enough space for maintenance around those racks, but not requiring any other space. We don't require a raised floor anymore. We could happily deploy if there was one there, but we don't need to put one in for this solution. Cooling, we still deliver 40 kilowatts of N+1 cooling by using an in-rack unit, so 5 in-rack units versus 2 larger crack units. And then, importantly, we're reducing the space that we're requiring to condition. So the space that we need to cool and dehumidify comes from about 135 square meters down to about 10 square meters. So significant reduction in the actual space that we're conditioning with our air conditioning systems. UPS, again, we're doing N+1 with an in-rack N+1 solution. We're still delivering the in-rack, the fire detection that they require, but we're no longer having to do it below the floor or for the entire space. And we're still delivering biometric access and so forth. So very similar specification, but some significant differences as you look down the list. So what it looks like, now this is, I'm not allowed to use a picture of the actual installation, but this is a very, very similar installation we did for another company where we're installing the micro data center into an existing room. We didn't need to fit the room out. There's no special fit out required. You still need to deliver electricity into it, but you no longer need to fit out the room with your redundant N+1 infrastructure for your electricals. You're dropping the dual feeds down into the micro DC. You need pipe work to get out to your outdoor condensers to actually get, to reject the heat out of the space, and you need network connectivity. Essentially, that's it. We don't need to fit the room out any more than that to get things up and running. And so the solution is very neat and tidy. Still looks nice, doesn't need a server room fit out. So here's the headline numbers from this specific examples. And I talked about these up front. And I'll drill in slightly deeper into the numbers in a moment, but the cost to build those two solutions, we were able to reduce it by 41%. And when you look at the next slide, you'll see it's a significant drop. It's a large reduction that makes a significant difference over the lifespan of the edge deployment. The 42% lower ongoing costs takes into account the two kind of headline numbers for them. One is the rent, reducing that room from 45 square meters down to 18 square meters has a big impact on their rental space. They're able to free up about 60% of the space that would have been allocated and use that for revenue generating purposes. They can use it for staff, they can use it for whatever else they want. Plus we can deliver a cooling improvement of about 15%. So the lower cost, and that we see that generally across the board in this type of approach, because it's so much more efficient, because we're cooling and conditioning such a much smaller mass of air, it's far more efficient to do so. The 12 times faster to deploy, that's very specific to this one. We knew it would take us about 12 weeks, 3 months, to deploy their server room, to build their server room on site with trades coming in and out, plasterers, electricians, and so forth. From order in the factory to build that, it's a week on site. We can deploy the micro DC, get them up and running with 1 week on site versus 12. So they're up and running much, much faster. And so the message there, I guess, is whether it's 12-week savings, what we often see in that edge deployment using a prefabricated or a micro DC type approach, you can bring your time to deployment down by weeks or months most times. We reduce the floor space. That ties into the ongoing operational costs. It's about 2/5. It's about 40% of the floor space required. This one I didn't mention up front. Because they're on a 5-year lease, they knew they would have to make good that room at the end of the lease. If you're leasing a building, when you leave the lease, generally you're expected to leave it in the same state that you took it on. So for them, there was going to be a significant tear down cost for their edge data center, for their server room. With the micro DC approach, there's essentially no tear down cost. There's a cost involved to bring some people in to move it out. That's about it. There's a bit of electrical work, a bit of pipe work to patch up, nothing more than that. So very, very cost effective. So the 95% was based on our quote to restore the room versus the cost to remove the micro DC. What that also doesn't take into account is we can roll that micro DC onto the next site. So then they can get the same next saving. If they're moving buildings, we can literally carry their data center onto the next site, reinstall it for them very cost effectively. So let's have a look at where the actual savings come from. So year one, over on the left, you can see obviously the big chunky number in green is the upfront cost to build the thing, to fit the room out, to bring in electricians and cooling experts and so forth. The saving there for them, it's about almost 100K British pounds. It's a lot in year one that you reduce the cost by. The ongoing savings, that the two main ones I mentioned, were savings on rental, savings on cooling. So you can see that is accrued across all 5 years of the ownership of during the lease. So they're saving around 26K every year, saving about 4.5K on their cooling costs every year, which is about 15% of what it's 15% less than it would have been. And then they're saving about 40K in year 5 in reinstatement costs or make good costs for the room. So it's some fairly significant numbers once you start adding up what the difference looks like. So the TCO over 5 years then looks like this. You've got in green, of course, the micro DC approach, and in orange you've got the traditional approach of what it would have looked like. The two things to call out, I wanted to call out on this slide, is the overall saving over 5 years is a touch under 300,000 British pounds. It's a lot of money that they've been able to save and put back into the business or not have to spend as an operational cost or CapEx cost. The other significant number is where's this line intersects. So your start point for the server room approach is here. You're almost at year 4 before you've met that requirement for cost with the micro DC approach. So that difference in approach has saved them a lot of money, got them operating faster, and made them more efficient with a solution they can carry on to the next site. So what does that look like in different industries? So that's a very simple example. I gave it as an illustration because I have the numbers for it and it's a nice one. But it also is, I guess, an illustration of what's possible in different industries if we just look at how we're building the edge and take a slightly different approach to it. So there's kind of 4, I grouped these in kind of 4. Some of the verticals come up in the different 4, as you can see. Space-constrained environments, rapid or standardized deployments, remote locations, and high-density requirements. So if we start with high density, I mentioned this one already. If you look at the university example, we see this again and again where a university wants to deploy a high-performance compute cluster inside an existing data center that isn't equipped to carry the heat load. So you can take the approach we did with the example I mentioned before. We're working with a university in Australia right now on an approach where they currently have their high performance inside a colo facility. So they're paying for the colo, their racks in the colo. They've got a leased line, a gigabit line, back and forth between the cluster and their campus. They've got their firewalls on site. The cluster is an NVIDIA cluster. So it's either 400 or 800 gig internal speed they've got a 1 gig link between the sites, so they're already bottlenecked massively between what the cluster is capable of and the site can receive and send. And then their firewalls are in the hundreds of meg. So their 1 gig link comes into a firewall that can't do 1 gig today. We know the cost to upgrade the firewalls is significant. Just to get them up to a gig, which is still way below what the internal cluster looks like, we could deliver them an on-prem prefabricated solution. We could build it for them, drop it onto campus with their compute in it for less than the cost to upgrade the firewalls. And then they would own it and they would have no bandwidth limitations. So being smarter about how you deploy the edge can really change that equation and deliver a better outcome in the longer run. Some other examples, I'll give 1 or 2 other examples as the clock ticks down. Remote locations, mining's a great one. In fact, you see this used in mining already. So for those of you who are involved in any sort of industry where there's remote locations, another great example for remote is local government. So local or regional governments where they need to have infrastructure on site. They may not have the budget to build a server room or build a data center. Being able to deploy a prefabricated or a micro data center type approach can allow that to happen far more cost effectively and quickly. You get the idea. The use case can be extended across many of these. I think telco is probably the last one. I did mention that up front. I love that idea for telco. If you think of all the telco locations around Indonesia or around your country that were built 20 years ago, 30 years ago, where there's now a push to deploy an MSC for 5G in an environment that wasn't built for it. The fit-out cost across all those sites is enormous. If you can deploy smarter at the edge, you take away that fit-out cost and you deliver the same outcome for the end customer. If you'd like to know some more about how you can build your edge smarter with a smaller footprint, just reach out to me. My details here. I'm walking around the show. It's pretty hard to miss me. So I appreciate your time. Thanks very much.
Andrew, we now have some time for Q&A. So if anyone in the audience wants to ask a question, please let us know. We've got a mic going around. Whilst we get started, I do have some questions for you, Andrew. My first one is around customization of these micro and prefab DCs. Do customers typically get something off the shelf, or do you have some engineering involved in these products?
Thanks, Audrey. So yeah, every design that we do is custom. It's bespoke every time. So while the solutions might look similar, and often they are very similar because an edge requirement is going to look similar, everyone has a different requirement around IT load, about what they're deploying at their edge location. So for us, we'll customize the design, which is the cooling systems, the power systems, and so forth, to match that. But we're also able to customize things as simple as how it looks. We can wrap your micro data center in decals to brand it for you, for example. We can do all sorts of things with the edge of it to customize specific to your requirement.
Thank you, Andrew. You've got a question?
Thank you, Andrew. In terms of procurement and deployment, the lead time from, say, concept to delivery on a ballpark basis within the region, what are we looking at?
So for prefabs, which is probably definitely the longer of the two, we would typically allow around a 4 to 6 month. For the single pod, we can deliver that pretty quickly in a couple of months. But for a multi-pod deployment, we typically allow sort of 4 to 6 months from order sign-off and design through to finish of manufacturing and shipping to site and installation. So that's kind of the time frame. Does depend a bit on how big. We can be a bit faster if it's small. Certainly with the micro DCs, that's much faster than that. We're down to a couple of months with that minimum. Yep.
Thank you. Any other questions from the audience, please raise your hand and we'll bring a microphone to you. Andrew, I've got another question for you whilst everyone's thinking about their questions. It's a question around resilience. So how do you ensure resilience in these smaller edge environments? Is there still redundancy?
Yeah, great question. Thanks, Audrey. So the short answer is yes. We follow the same design process or the same design principles that we would if we were building a traditional sort of data center design. So whether we're following TIA 942 or uptime. Our team is certified to design to whatever tier level is required. Typically, we're designing to tier 3 is what we're most often asked for. We do some tier 2 designs. We get asked for tier 4 designs. We don't typically build them because when people see the cost, like that in most scenarios, there aren't a lot of tier 4s built as many as people would like to think because they are quite expensive to build just with redundancy. But we are able to build the redundancy level required into any of those solutions. Yep.
Perfect, thank you. I want to ask you questions around scalability. So can this model scale? And for example, if you've got an organization that's starting with a single micro DC, can they then expand later?
Yeah. So both approaches, I guess the micro DC, absolutely. You can start with a single rack. You can grow that out to a second rack. Knowing how big it's going to get helps us from a design perspective. So which kind of air conditioning solution we're going to use, for example, whether it's an in-row or in-rack type solution. So the expansion can be done and just added to simply as long as you have the space. With the prefabricated approach, there we can expand. It's critical then to know what are the long-term plans because it affects how we'll design the modules. So that's, I guess, in terms of expansion. In terms of scale, how well they scale, if you look at prefabs, the example I showed you before with the single module, that was about 9 or 10 racks, that particular example. So they could be a handful of racks, they could be sort of 20 racks. We're building one right now that's, I think, around 300 racks using that prefabricated modular. That's kind of that's how big we can get, or anywhere in between. With the micros, you're typically looking at anywhere from 1 rack through to sort of 20 racks. You're not really looking at much bigger than that. You're thinking about a different type of build or a prefab approach beyond that. Yep.
Perfect. Thank you very much for your time, Andrew, today. That wraps up our session. Thank you, everyone, for listening.
Thanks, Audrey. Thanks, everyone. Talk to you around the show.
Hello. Hi, everyone. Welcome back to the Tech Showcase. I'm going to move swiftly on so that we can stick to time. It is my pleasure to introduce the next session, Advancements in Data Center Battery Backup Technologies. And we have Eric Hill, Director of Global Marketing and Product Management at CSB Energy Technology, who'll be talking us through it this morning. Eric?
Thank you for that. Good morning, everyone. Oh, very good. Yeah, I'm going to need that. So again, thank you, everyone. My name is Eric Hill. I am the Director of Marketing and Product Management at CSB Energy. Been in the battery industry for almost 20 years, doing a various amount of applications, broadband, telecom, renewable energy, data center. And yeah, happy to talk to you guys today about some cool things we're working on that's really going to, we think, innovate the space and help with some of the challenges today in data centers. So first, let's talk about our first product that's really going to help with cooling and help preserve battery life in that elevated heat space. So it's no secret data centers are getting hotter, right? Up to 86 Fahrenheit or 35 C. Sorry. And in most countries, it's going to be upwards of 12% of the total power consumption, right? For a data center. And you have different types of cooling, right? Free air, liquid, immersion, hot, cold aisles. But they all require different levels of power. Excuse me. So as you increase the power, you increase the heat, you increase the space, and you're taking up a lot of space around that sort of environment. So again, 25 to 40% estimate is spent on cooling in a data center. Average temperature increase is going up. 50% of operational costs are projected to be part of cooling. And it's anywhere from $1,000 to $2,000 US per kilowatt to cool a data center. So again, If we don't do anything about this and we just continue to scale like this, there's going to be significant challenges in a data center when it comes to all your equipment, but especially batteries. Because heat is the #1 killer of batteries, as I'm sure everyone's aware. So we have this cool new product, Calor XHT. You guys may have seen it in our booth over at #2. XHT stands for extreme high temperature, right? So this battery is more than just another run-of-the-mill, sort of solution off the shelf. It's very unique in the fact that we are the first to market with a high temperature, high rate battery. There are a lot of high temperature batteries out there today, but they're more geared toward energy, longer duration discharges when you go beyond more to an energy source. This is focused on power, 15 minutes and less, right? Typically when you discharge a battery below 15 minutes, it requires a lot amount of power and it's going to take a lot of power. We've combined a few different technologies inside here using pure lead with a combination of catalysts and a special type of plastic material on the jar that allows it to survive in an elevated temperature. 25C is kind of the norm, right, for a battery room or battery application, if you will. And for every 10 degrees C you go above that, you typically have the life of your battery. Well, now you can go to that 10 degrees C and not sacrifice battery life. And the cool thing about this is it's very, very power dense. In a typical 480 volt DC application, you can fit 0.5 megawatt in a traditional battery rack. 0.5 megawatt of power, that's a lot. So some performance benefits here on the testing that we've done. That graph on the left that you see over there, service life, the typical red curve is what a typical VRLA looks like in a high rate application for service life. But you notice the green life, how we significantly extend that overall service life? That's because of our exclusive internal Catalyst 2X technology. It's a small little device that goes on the battery itself, and it just helps basically keep it hydrated internally so you don't lose internal power, have a short, whatever happens inside the failure for the battery. Prevents thermal runaway. It boosts charge and discharge efficiency, right? So you can maintain that service life in an elevated temperature. Also, too, I mentioned the plastics. So a lot of the VRLA stuff today is standard PP or V0, which is a flame retardant case. But we use a special PC ABS case right here, which you can see the deformation rate goes, it gets a lot stronger, a lot harder. So in elevated temperatures, plastic, it'll, mold and permeate. Whereas this one is much more robust. And we've taken it through significant temperature testing all the way up to 100 C. But this one goes to 80, and you can see the significant difference in deformation. So the plastic really holds up well. Excuse me. And like I mentioned too, we are the first one to do a high rate, high temperature battery. And compared to other high temperature battery offerings on the market, we have the most power density. So the feedback we get from our customers a lot is we want shorter and shorter run times, but more and more power. Okay. So what we've done is we've really perfected the extreme high duration, high power, short duration discharge, 5 minutes or less. Right. So you can see the significant gap in performance between other high temperature batteries there. Again, we talked about a little bit about that Catalyst 2X technology I showed you guys. This is data on what we call float current. So when your batteries are just sitting there waiting to be discharged on emergency backup, they're always topped off, ready to go at any given time. Well, traditional batteries, you leave them on float current. You have to elevate that float current to keep sulfation off the plates and make sure they maintain service life. With this technology, you can lower your float current on the batteries. Again, that improves service life. So what that means is with our internal catalyst, it's keeping hydration internal to keep going. So that way we can handle higher temperatures. As the temperatures go up, this stuff scales back and your life significantly decreases. So again, what does that mean for a data center operator to have a high temp battery? Well, it can potentially reduce your cooling demand, right? I know batteries are mixed with UPS equipment and whatnot too, but batteries are typically the most sensitive to heat. So it works reliably in warmer environments. You could potentially, depending on the scale of application, cut your energy use on cooling. You need fewer battery strings, so you can reduce your battery footprint with this battery. You don't need as many traditional cabinets, say in a traditional lead acid space. And again, smaller footprint, lower installation costs. So there's many significant benefits to the battery. So now I'm going to talk about the next one, which is more in the line of advanced energy storage beyond the traditional stuff. And the most common question we get all the time is, well, why do I need an advanced battery, right? Well, there's several reasons. The applications are changing, right? It's no longer an emergency backup. It could be demand response, frequency regulation, whatever, right? So that means more rolling blackouts, more rolling power loss, things like that. And a traditional emergency backup battery doesn't support that kind of application. You're going to kill your battery very, very fast. You need something that scales with demand, right? So you need batteries that can be modular in design, and you can add to the footprint when needed, or potentially have batteries that are ready to go but not necessarily using them. So again, modularity, it's got to scale with the footprint. And speaking of footprint, physical space is at a premium, as we know, right? So you need a smaller scale but maintain that higher power density. It's a big challenge in the battery industry for us as manufacturers is how do we reduce the footprint but also maintain that power density? It's very, very important. Safety, right? Safety is paramount in everything we do in the battery industry. Higher power means higher levels of safety needed, higher voltage levels, higher current, higher amperage, could lead to catastrophic thermal events. So on a wish list for a battery, right? Small footprint, you can cycle to meet the changing applications. Modular design. One point I didn't touch on, but it's very important, is sustainability. Are the materials used inside your battery able to be recycled? Can you reuse them in other applications? And most importantly, in my opinion, safety. It's safe to operate. You can use it as needed for any sort of data center application. Well, thankfully, we have a solution that is called PowerBox. It uses a lithium iron phosphate technology. The key advantages here, because there are a lot of lithium-ion solutions on the market today, but we've done things a little bit differently, and we've really focused on safety and power for this application, right? Most lithium-ion applications today for high power stop discharge around 10 minutes, between 7 to 10 minutes, right? We push that a little bit further and go to 5 minutes, which also increases power density, right? So now we're up to 320 kilowatts per rack at the 5-minute rate. Really what we talked about safety as well too. There's 3 different levels of redundant safety inside this battery, meaning that we start at the cell level with UL 1642. We go to the module with inline fuse protection and individual fire suppression on each individual module. And then we also have a multi-powered BMS that's both AC and DC combined, so you can run it either from the battery or from your AC grid. And this is coming really soon. It says June. It's probably a few weeks off, more like July. But this will be right around the corner. I know it's smaller than I thought it would be. But again, what I talked about, level 3 BMS, pack level protection, all the necessary safety certifications. It comes with the UL 9548 test report. That's really growing in importance. It's mandatory for where I come from in the US, and certain pockets of APAC are starting to require it now too. We have the integrated HMI with battery monitoring intelligence that can be done remotely or on site, so you can see all your settings and parameters of performance. And again, it's modular, right? So it's small footprint. It can go stack up to 8 per UPS, so you can scale up to 2.5 megawatts per stack. And it can be used across a various number of applications, whether it's data centers, hospitals, rail, C&I, government, anything that really requires high power for a UPS. So again, the cool thing about CSB, what we do is we serve a multitude of applications, but we're really focused on the data center from small scale, small enterprise, edge stuff, all the way up to hyperscale, right? So we have a battery that can fit your needs. And if you guys heard me in my talk yesterday, and my other colleague Jeffrey, we talked about what do we do for the data center industry? Well, we start with the question, what? Right? What do you want your batteries to do? That's not a really common question asked, unfortunately. And that's where it really needs to start, because we have a multitude of applications, as do all battery manufacturers, though, that can serve your need. And there is no one perfect chemistry, right? So there's a lot of different chemistries that can solve problems better, okay? And why would you use us? Again, performance, support, commitment. Those are our 3 pillars, right? So we, again, dedicate by application. We're all over the world. We're based here in APAC. We manufacture in Taiwan and Vietnam. I work in the US. We have a big presence in the US and in Europe. Support, we're all over the world. Again, we stock everywhere. And commitment, we scale to production based on your needs, a lot of support, and our competitive pricing per scale. So that is pretty much it for me. If there's any other questions, I'm happy to answer anything on batteries or about our products. If there's anything, please fire away.
Great. Thank you so much, Eric. So before I kick off with my questions, are there any questions from the audience? Nope. Okay. Well, have a think. You can put your hand up while I ask my questions then. So, Eric, what is the ideal battery technology a data center operator should choose?
Oh, that's a great question. And I'm going to give you the typical answer that any battery manufacturer should. It depends. What do you want your batteries to do, like I just closed with? Are you an emergency backup? Lead acid might be perfect. Are you going to do a lot more cycling? Lithium ion probably makes more sense. Or there's other, advanced cycling technologies. I know some of my colleagues at Toshiba are here as well too. They're going to talk about lithium titanate. That's a great technology for extreme cycling and extreme power. So yeah, it really depends. We see it as kind of a two-horse race between lead acid and lithium ion, but there are a lot of other chemistries out there that are coming to market. And again, I've said it numerous times here, but I truly believe it is that there's been so much innovation in the battery space in the last 5 years that it's just hard to put my head around. So you really, really do the homework and understand what your battery can do for you. Sorry, it's a long-winded answer.
No, that's fine. Next question. Is there anything CSB is doing beyond the traditional electrochemistries for battery technology in the next few years?
Oh, that's another good one. Yes, there is. We're looking at all options, right? Staying with electrochemistry, we're talking about looking at innovations to lead acid. I know that sounds counterintuitive. It's a 150-year-old technology, but there are advancements that are coming. There's a technology called bipolar, where we significantly reduce the footprint and the weight, but it dramatically improved the cycle life. We're always looking at lithium ion advancements, solid state, sodium ion, things like that. We've also taken a look outside the scope a little bit too, around hydrogen potentially or geothermal stuff, just to kind of see what might work or scale. Nickel's making a comeback all of a sudden now too, so there's some nickel stuff that we might take a look at. But yeah, we're definitely very much an open book, and we're exploring as needed to find the technology that scales best for the customer.
Great. How does CSB see the battery deployment trend in the next 3 to 5 years?
Man, we're just getting hit with these good ones. It's gonna elevate. I mean, it's gonna go up. It's gonna continue to rise. Especially with the increasing power demand, increasing change in application. We see a lot of requests now for DERs, demand, basically demand response sort of assets that get deployed at the data center to support peak loads. Because frankly, some of the data centers aren't waiting for the utilities to catch up. And so they want to protect their own power, protect their own assets, especially when they write these contracts to customers that guarantee uptime. They have to guarantee power. The other factor that we see is that renewables coming onto the grid, which is a good thing, but it creates a lot of frequency problems. So when you have voltage sags and spikes, it's going to continue to create frequency disruptions. Even a microsecond can take down an entire data center if you're not properly hedged with a battery bank or super cap or whatever. So we try to educate customers and tell them that the battery's there to protect you and protect your asset and maintain your operations, but it's important that you do it smart. So yeah, we see it just continuing to go for the next 3 to 5 years exponentially globally.
Great. I just wanted to check one last time. Is there any questions from the audience before I wrap up? Oh, over there. Sorry,
right.
sir. I'm going to have to hand you this.
I do want to come back to the sodium as an emerging technology, because so often in the data center space we see flammability of being the key hesitating factor for going to lithium, right? Do you think that your emerging lead acid technology advancements will offset sodium, or is sodium the way forward?
Oh, that's a good one too. Sodium, is I think going to find a place just for one of the reasons you just talked about, but also too from a sustainability standpoint, right? I mean, there's so much abundance of Na material in the world. It's from what I've heard in my recycling days, they're still trying to figure out how to process it to extract that material at end of life. So that's a challenge. But the safety element is really going to be the key thing there, right? There are slight performance trade-offs when you go from a sodium to a traditional lithium carbonate battery. It's very small though. But yeah, I mean, I think there's going to be a place for it. Some of the big lithium guys are working on them now. I think what's going to really matter there too is scalability. Can they build it at the same cost and same production time as a traditional carbonate? So yeah, that's going to be some challenges that I see. But on the lead acid side, advancements wise, it's going to be again, it just comes down to the application, right? I mean, lead's always going to be really good for high power, extreme high power, because lead's just so robust and abuse tolerant that it can tolerate the ampacity and the inrush of current, whereas lithium ion not so much, right? Or sodium, because once you go below 5 minutes, it really, really, I guess it just doesn't perform because the BMS is going to kick on and shut it off, right? So it comes back to my answer, it depends. There are advancements that are happening in lead acid, but ultimately, will it maintain the power? Yes. But for cyclability and for energy density, lithium ion is still king.
Great. Oh, another question over here. Sorry. Here you go.
Hi. I just wonder, using the lithium LFP, right? LFP.
Yeah.
I just wonder about the safety for the thermal runaway. How to deal with that?
Another good question. So for our product in particular, I mean, we have a 3-level BMS that starts at the cell level. So we added a lot more thermistors to detect temperature, to sense a potential thermal runaway event. But we start at the cell level, we go to module, and then we go to system, right? And then we start from there, and we have individual fire suppression on the module itself. We have inline fusing on the pack itself. We have AC-DC conversion on the battery pack, so the BMS always maintains power. But we've engineered it to have multiple redundancies. So if one fails, it checks down to another, checks down to another. So you got to have a lot of things happen in order to get to that point. But as far as thermal runaway goes in general for lithium ion, I mean, it's typically maintained, by a BMS, but it's very sensitive to temperature, right? But once you cross that threshold, there's no stopping it. It'll just continue to go into thermal runaway. But that's at the core of what we talked about with PowerBox, is safety, right? Because there are a lot of concerns. The safety standards are changing constantly, and we're very conscious of that. And so that's why we might not be the cheapest solution. My sales guys are going to kill me if they heard me say that. But we wanted to give our customers peace of mind that when they deploy this system, they can sleep at night knowing that it's very well protected and very robust.
Great. Any last-minute questions from anyone? So obviously we know CSB have a stand here on the show floor where I'm sure they can answer any questions anyone has. But is there any other way that you recommend that they get in touch with you or your team, Eric?
Yeah, another good one. You guys can get me on LinkedIn. I'm very active on there. Just type in Eric Hill CSB. You'll be easily find me. Our website, www.csb-battery.com. And we have a big team here. We have some of my engineers here as well, too. We're back at booth 2. So, yeah, feel free to stop by, ask us any questions, and we'd be happy to help you.
Great. Well, thank you so much for your time this morning. Eric, a round of applause, please.
Yeah. Okay, good morning, everybody. Just about still the morning. I would like to introduce now the next project showcase, looking at navigating the supply squeeze and securing critical electrical equipment in a high-demand market. I'd like to welcome to the stage the speaker. We have Paul Lee, who is Director of Strategic Segments for APAC from Chint.
Hi, good afternoon. Yeah. So my name is Paul. I'm part of the Chain APAC team based in Singapore. So just a little bit about myself. So I've been in the industry for some time now, the past decade. So I specialize working with the customers in different segments. So I'm a strategic segments director of our Chin. So we support some of our customers in different segments. For example, in utilities, in renewables, and data centers, of course, right? So today I'm gonna spend a little bit of time talk about the other segments or the other verticals that Chin is in that actually affects how data centers environment will be in the next couple of years. Okay, so and I will start with this interesting article in the news. Actually, this was just recently, a couple of days ago, right? So this was in the Financial Review, and if you look at what this journalist was saying, there is a runaway energy build-out cost threatening data centers built worldwide, right? So, and one of the key problems or the challenges that this journalist mentioned is really the equipment supply chain issues that is revolving around this segment, right? So, equipment supply. What are these equipment supplies that we will be sharing a little bit more later? Okay, and then this one here. This is from McKinsey. You can see exploding demand and lagging supply for data centers globally as well. So there is really a key challenge. And today, I heard about some of the panels. They're talking about the three challenges, right? People and power, and of course the planet. So these are some of the challenges that Chin tries to help our customers to tackle and also to overcome them. Like what I mentioned, so the three verticals that Chin is in. Other than data centers, we are heavily involved in renewables and also in power utilities. So I'll share a little bit more about our involvement globally, not only in Indonesia, but also in the APAC and also globally in Europe as well. So if you see some of these key interesting parameters, data centers are getting quicker and quicker to execute, right? You're looking at about 1, 2, or 3 years just to even come up with the data centers. And if you look at the environment, for renewables energies, right, there is a little bit of disparity within the built time and the speed, and of course electrical systems that a lot of data centers are having issues with to power their data centers. So you can see the disparity, and that's where the equipment supply and the speed to market really matters for all these projects. But before I go into all these challenges, I just want to spend a little bit of time just to share who Chin is. So we are a smart energy solutions provider worldwide. So we are actually in all over the world in 140 countries. So our markets are not only in APAC, but also in, for example, in Europe and in North America as well. So we are a $25 billion company. So worldwide, we are supplying to a lot of electrical equipment to our partners. So from high voltage, medium voltage to many different electrical systems. We are also part of the green journey. Worldwide, we are part of the United Nations Global Compact. So our DNA is really to help our customers, right, to achieve sustainability as well. So some of our achievements, we have actually powered quite a tremendous number of projects worldwide in renewables power and working with utilities to connect and also to power to our customers. We are, like what I mentioned, 140 countries worldwide. So other than Indonesia, we actually cover quite a fair bit of countries in APAC. So APAC, where I'm from, we cover 20 over countries in this part of the region. And if you can see in Europe, we actually have a huge presence in the European market as well. Just last year, we were one of the top or number one exporter of transformers into Europe market. And our offering and our solutions cover from the generation, utility, all the way down to your consumer. So you can imagine the wide portfolio that we have. So in terms of generations, for example, in solar, inverters, in terms of even the new tech as well. Touch a little bit about the new tech in terms of hydrogen fuel cell that we also have developed through this past few years. And of course, the bread and butter, our high voltage systems in terms of the switch gears, transformers, medium voltage, and we are now into a little bit more advanced, for example, in prefabricated. I think some of the speakers I've already talked about and touched on the prefabricated portion. And of course, in the low voltage systems as well. Okay, so let's get into it. Okay, so I mentioned about three verticals: renewables, utilities, and data centers. So what's happening in the renewable space in the world? So if you look at APAC, APAC actually accounts for a big majority of the renewables power that will come online in the next couple of years. If you see here, this is actually the orange, okay, not too clear. The orange part is actually APAC, where they will add on the additional renewables power into the grid. So we are looking at 67 gigawatts of power that's going to come online in 2025. And you look at the numbers, that's tremendous. If you look at it versus, for example, data centers are going to come online, the power that is required for renewables is actually much, much, much more, right? And if you can see, we also talk about, I think some of these panels have also mentioned, right? The powering facilities like data centers, right? They are signing a lot of power purchase agreements in the region and also globally. So you can see there is a growth in the customer's perspective as well to acquire green power for their facilities. And that is, just, you can see the trend as well going up. I bring it back to APAC region. APAC region is going to see a tremendous growth, and one of the key initiative or projects that you will see in APAC is really, one of it is regional power imports. So this you can see, you're looking at about 6 gigawatts of renewables energy to come online in the region and powering where? To Singapore. And they're going to build a lot of this kind of solar farms in the region. And they've already awarded to some of these suppliers as well, these operators as well. So EDPR, Keppel, those are some of our very close partners that we work with to supply some of this equipment. And if I do zoom in some of these projects, what actually are we supplying to? So I take one example. This was a 1 gigawatt solar project. I wouldn't name the name, but this is a pretty big site, the 3,500 hectares, right? And you can see the scale of this, 3,500 megawatt peak solar panels, together coupled with 4,500 megawatt hours of BESS. So this is a tremendous, huge project, just for 1 gigawatt. Just now I mentioned 67, right? So you can imagine how much electrical equipment goes into these projects. So if you look at this, these are some of the electrical equipment that goes into these projects, from solar panels, inverters, low voltage, all the way up to the high voltage systems that powers all these solar farms. So you can see, I will start to highlight some trends, right? You can see the electrical equipment, those are being powering these solar farms, okay? And this is not only in APAC, you see this trend all over the world. So our projects, our business, not only in APAC, so you can see all these solar farms that have already come online and will come online globally as well. So you can see this trend going up, a lot more electrical equipment being pushed into the market to supply to all these solar projects. And the next trend, you know, we talk about alternative energy, right? There's talks about, for example, nuclear, right? I think one of the alternative energies that a lot of people are looking at is also on hydrogen, right? There are many challenges with hydrogen at the moment, right? But at Chin, we are actually developing, we are actually very forward thinking. So we have developed solutions into the hydrogen space as well. So we are part of this whole fuel cell electrical chain, from the power systems, even conversion electrolyzers, the full chain of solutions from Chin itself that can power up this fuel cell generation. So for example, we have already developed a megawatt scale fuel cell generations for projects. We've actually deployed this for some of our customers that looks at carbon capture as well. So how do we generate power from this excess waste that's a big use in your sites? So these are already deployed in projects worldwide. So you can see a trend. And when people start to adopt all this, you can imagine the number of people that will go into this kind of a technology as well. And I look at the utilities. So I talk about renewables being part of the bigger macro that's powering all these projects. So they are also being connected to utilities in this region. So if you look at some of these interesting news articles, right? In Indonesia and Malaysia, in Thailand, right? The utilities are very aggressive in growing. They see the population increasing. They see the load coming online from data centers, from many different industries. And Chin, because we are in this vertical, we can see what is happening in the industry. So you can see Indonesia, 71 gigawatts will come online, right? And Malaysia as well, trying to have renewable energies into their grid. So they are also aggressively growing their grid, having more farms, upgrading their existing infrastructure. And of course, Thailand, right? Thailand is looking at, if I recall, 70 over gigawatts as well that will come online in the next couple of years. And if you see the trend here, Indonesia, Malaysia, Thailand, right? These are the key major markets that data centers are going into right now, right? So you can imagine the amount of equipment and the resources that will be required to power your renewables, to power your infra for your utilities. And of course, if you look at the equipment, just now I show you the first picture, right? The equipment spread, something familiar, right? So all these electrical equipments also go into the utilities that gets connected to the grid. So you can imagine the amount of demand for all this electrical equipment will start to go up more and more. And we're actually facing some of this in other parts of the world, for example, in Europe, which I'll share a little bit about. And of course, lastly, I think I don't need to touch too much on the data centers. I think everyone is very clear where this industry is heading. In terms of the growth, APAC, we are looking at the 2.2 times more growth that's come online, right? We're doubling up what is existing and growing even more with the next coming years, right? And if you look at the trend, AI, right? So a lot of this growth in terms of the rack power, I think many panels also have talked about this. More power is required, right? In terms of the AI revolution. And if you look at the equipment that is being put into these projects, they are getting bigger and bigger in terms of the ratings. You talk about your low voltage, you talk about high voltage, they're going to higher, and they are in the space of renewables, in the space of power utilities already. So all these different segments are vying for the exact same kind of equipment in the market. And if you look at the average growth of the data centers, right, those founders or the early pioneers in data centers, we started off with just 2 megawatts, 3 megawatts, or even lesser than that, or what we call computer rooms, right? And now we are going into the 500 megawatt or even higher megawatt territory for data centers. So you can see this tremendous amount of growth. And that is where you can see where we started 1 megawatt, probably just low voltage. And right now you're going to see a lot of projects that's going for the 100, 200, 300 that will look at a lot of the high power equipment as well. So all these three verticals are colliding in the same space, requiring the same kind of equipment in the whole electrical industry. So how do we tackle this supply squeeze in this day and age, right? Where everyone is vying for the same thing. And I just want to share some strategies that some of our customers, right, not only in APAC, but also in Europe have also adopted and work with us to help them expedite this and solve this challenge. So number one, right, we're looking at the global frame agreements to lock down on our factory capacity. So this synergy between the customers and the manufacturers needs to be in place, right, to tackle some of these supply chain crunches that will be coming. This is a good example. This is Enel, the world's third largest utilities provider. So they are heavily involved in upgrading their network, whether be it in putting in the renewables and upgrading the existing network. So we've partnered with them for the upgrading systems, and we have supplied electrical equipment, you can see. So from high voltage all the way down to the individual accessories, the HV components as well. And we actually signed a 3-year agreement with them, right? So what this does is it lock down the factory capacity and make sure that the projects are running faster with a shorter lead time. We can actually able to deliver much faster than what is normally available in the market. So this helps the customer to deploy their projects much faster. Just now I mentioned, right, the timeline of utilities projects can go up to 5 years, 7 years. And this helps them to reduce some of this timeline to be deployed. So just some examples, we have done this in Germany. This was with another utilities, Italy. And even in data centers as well, we are also working with Italian data center operators, right, to how do we lock down some of this manufacturing capability or production, right, for their fast-paced project. Now, number two, I'm going to look at this, really look at how do we have a global and a local strategy in terms of manufacturing. And that is in line with Chin's localization strategy globally. So if you look at Chin's portfolio of factories in APAC, I just zoom in APAC, right? So we are actually having a lot of local factories all over the world in APAC, and Singapore, Malaysia, Cambodia, Indonesia, Thailand. So you can see here we are seeing the growth in Indonesia, and we are gonna increase our factory capacity in Indonesia as well. So 2 new factories will come online just this year. And this setup is also supported by our global factories in China. And these factories are our full automated factories that we'll share a little bit. And an interesting case came about during COVID, where a lot of countries were having different lockdown periods or different kind of lockdown, right? So there was a lot of resistance, a lot of challenges to actually bring our products to the customer. So our network of factories enables us to deliver actually these projects on time, right? So we were able to, for example, there was a project in Singapore, right? So we utilizes our factory capability in, for example, in Vietnam and in China to be able to integrate and also deliver these projects to our customers without any effect, right? Because some countries, different lockdown, you can't go to the factory to work, you can't go to the port. So all these challenges with our spread of factories, we were able to tackle. When I mentioned, right, factories, so Chin is also using an AI factory automated solutions in our factories. So fully automated, we are one of the world's largest low voltage manufacturer. So these factories manufacture 3 million poles a day, and is only run by 6 to 7 people. So you can imagine the amount of automation that goes into this, from raw materials all the way down to warehousing to the ports itself, fully automated. And that allows us to cut short the lead time in terms of our delivery to our customer. And lastly, adopting prefabricated solutions. I think this is something that's also being shared with some of the panels. This is something that is moving ahead. We see the trend. So instead of using multiple equipments being spread out, we are actually adopting a prefabricated solution, something like this, housed in containerized solutions. So this cuts down the on-site cost for labor, especially for some of the works, for example, in Australia. We see the cost of labor on-site is rising as well. So all this can be done in the factory, integrated, and then delivered to site as a whole solution. And the on-site works, time taken is only the connection of, for example, the cables to these prefabricated solutions. And it can come in a variety of different solutions with medium voltage transformers, low voltage switch gears, UPS solutions, batteries. So depending on the requirement, we can customize a prefabricated solution for our customers. This is another one that is an integrated prefabricated power skid solution. So integrating transformers, switch gears, UPS into a whole skid solution that allows fast delivery and reducing on-site labor costs as well. So very quick delivery. We delivered this for some of the projects in Indonesia. I think from drawing to FET was about 2.5 to 3 months, if I recall. And these are some of the solutions that a lot of customers are now exploring to adopt to reduce the on-site execution time. And this is actually integrated in our world global factory in China. So you can see this huge factory has our low voltage factory, our medium voltage factory, and our integration factory all at the same place. That allows us to build this equipment in our factory floor at the same time, right? So our manufactured transformer switch gears are all put together in our factory in the same area. Another example, this was a project in the Philippines where we executed a prefabricated solution, right? You can imagine the savings and the time that we were able to help the customer to achieve, to reduce in terms of the on-site execution. This is an interesting one. So this is, I mentioned we are in a lot of the different verticals, right? So this is in renewables, right? This was executed with the Singapore government. They were looking at energy storage solutions to build. So this was a 200 megawatt energy storage solution, the first in the APAC region to be deployed. We were able to help the customer to reduce the time. So the whole entire project was actually cut short from project execution to handover. It took 6 months. And this was actually in the news most in 2023, recording this. So the largest and the fastest delivered containerized solutions projects in the region and possibly in the world as well. So yeah, so I share a little bit about the strategies. So hopefully this is something that is talking point that you can take back and then also to explore. So we are actually in booth 67. So if you have any questions for me after this, right, we can have a more in-depth discussion. But yeah.
We also thank you so much, Paul. I think you shared some great case studies and a lot of different solutions to the supply chain challenges. Does anyone on the floor have any questions? So one from me, I mean, you really touched on adopting global trade agreements, but that process must be quite complex. What are the key challenges and considerations when you're looking at global trade agreements?
That's a really good question. So it's not easy to implement a global kind of a frame agreement or to lock down on the equipment because there's a lot of customization and changes along the way of project execution, right? So what we can see is there are different strategies. For example, you can look at the locking down on, let's say if you're deploying on different countries, right? Different countries have different voltage ratings, different countries have different requirements, right? We can cluster some of these countries together and then standardize some of the solutions for this kind of agreement itself. And of course, one of the key parts for this to work, right, is really standardization of your requirements, right? Big organizations are actually going to that direction. For faster deployment, they are standardizing their designs all across APAC, all across the world. And that helps in terms of the speed as well, in terms of the equipment procurement. Yep.
Fantastic, really interesting. You also touched on in your presentation renewable energy. How do you see renewable strategies evolving as a solution to these supply chain challenges?
Yep. So I think everyone is aware renewables power is getting cheaper and cheaper, right? More competitive. It's almost to a sense like it's a sense and commodity as well. So solar is already at the limit of where we can achieve, and new renewables are going to come online, right? For example, hydrogen I've talked about, and these are some of the things that once we overcome some of the challenge, for example, like hydrogen delivery, and these are some of the solutions that will be in huge demand in the coming years as well. So in terms of the adoption, so I would say that in terms of operators, you should start to look at some of these alternative energies really quick so that you can do your pilot, you can do your case studies, and then fully deploy before the whole market starts to move into this area. Yeah.
So let's get ahead. Get ahead.
Yeah.
Okay. And then looking ahead, obviously you've talked about some of the markets already, but what do you think are the next key markets that, you know, if you're thinking much more proactively about how we get in front of the supply chain challenges, what are the next key markets that you think we need to have our eyes on?
Cool. So I think you can see some of these markets in the news, right? Malaysia, Thailand, right? Indonesia. So these are some of the key markets that Chin also is positioning ourselves. Like what I mentioned, we're having our local factories being put into local countries as well to expedite this. For example, in Thailand, we have low voltage factories. Also, there's a supplying to the local projects and markets already. So these are some of the things that we want to help our customers, right, to have a faster delivery, to cut short the execution time. Yep.
Fantastic. Any other questions from the floor, just before I move to my final question? I guess a bit of a provocative question, but with the prolific acceleration of AI, do you think the industry can really keep up, and how?
This is a tough one. I mean, if you have listened to some of the panels in the morning, right, they're talking about potentially even 1 megawatt of server racks, right? Just one server rack with 1 megawatt, right? So this is going to be a challenge in terms of safety, in terms of powering all these servers. So you can see the power density will keep going up and up and up and up. And all these electrical equipments will need to catch up in terms of the size, in terms of the footprint, and the speed to market. So we are actually, the market is way ahead of a lot of what the supply can do right now. Yeah, and so I think that's something that we need to work very closely with our end customers, our operators. How do we work together to tackle some of this supply chain crunch, right? And to deliver some of this at the quickest possible time.
There's a lot of complexity, so
Yes.
collaboration is key.
Yes.
Okay, that's wonderful. Thank you so much, Paul. I've really enjoyed your presentation today.
Pleasure.
Thank you very
Pleasure.
much, everyone.
Pleasure. Thank you, everyone.
When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool.
Are we on? You can hear me okay? Perfect. Good afternoon, everyone, and welcome back to our afternoon sessions here at the showcase stage. Next up, I'm delighted to welcome Vuon Yip Seng, Senior Manager from Munheen, who's here to discuss with us leveraging the risk of downtime with Type B EELR. I will hand over to you now, and Vuon Yip Seng will go through his slides, and then we'll have time for some Q&A from the audience. Welcome.
Thank you. Hello, good afternoon, everyone. Yeah, my name is Vuon. Can you hear me loud and clear? Okay, so a bit self-introduce. A quick introduction about myself. So I'm an electrical professional engineer in Singapore, also the licensed electrical workers. and as well as a certified energy manager in Singapore. So a bit of background about Manhin. So we are the electrical solution providers in Singapore and also in Southeast Asia. So we do provide a solution for power qualities and electrical protections and lightning protections. So the topics that I'm going to deliver today is about the how I'm going to lower the risk of downtime with this Type B ELR itself. Yeah. So feel free to ask questions if you have any queries. I hope to make this the whole sharing sessions a bit more lively. Okay. Yeah. Okay. So before I go in details, I want to talk about the overview of electrical safeties in the data centers. So some of the key hazards that we can see in data center actually is like electrical shorts. So like example, you have a fault in the system or fault in the equipment itself, it will cause electrical shorts. And then it might also have, it has a risk of fire and arc flash, and also leakage currents. And leakage current, particularly this leakage current is very important. Reason being, a lot of these IT equipments, for example, the SMPS, switchboard power supply inside the IT equipments itself, or the VFD drive, UPSs, these kind of things, these equipments actually emits a lot of leakage currents. So some of the safety measures, the first one in electrical installations, we need to actually make sure that we have a proper groundings and bondings. Okay, this is essential because without a proper grounding and bonding, and the protective device, the second measure, it can't pick up, it can't detect, it cannot detect the fault itself. So when it cannot detect the fault itself, it cannot react on it. So the second measure is we must have a proper protection devices, and leakage current is one of that. And third, we need to have a regular thermal imaging or maintenance. This is actually to keep your protective equipments working in a well conditions. And lastly, we might also have the mitigation plan for the arc flash. Example, maybe you need to do some arc flash study and then to implement some arc flash mitigation plan, or have to decide some proper PPE for the electrical installation or electrical works. Yeah. So the important earth leakage protection relay, first, it provides an additional fault protection. This is going to do is like, it provides the additional benefits of protections to a user making direct contact with a live conductive part where other methods of protection fail. This is actually an additional protections. And the second importance of this earth leakage protection relay is actually to protect against the fire hazards. Because if the system doesn't have these earth leakage protections, right, with this leakage current prolonged leakage current in the system may cause fire hazards. So that's why it is very important to have these in the system as well. So next, I want to there are actually 4 types of earth leakage protection relays, or we call residue current devices. Okay, there are 4 types. So today what I'm concentrating on is a Type B. Okay, so Type B is actually the protection relay that's the Type B ELR is a protection relay that it can react on these AC leakage currents up to very high frequency. We talk about 1000 hertz. Okay, our fundamental frequency is 50 hertz. So when we talk about high frequency, it's 1000 hertz and above. So a Type B can actually react up to 1000 hertz, so equal to about like 20 orders of harmonics, 20 times of fundamental frequency. So it also can react on the pulsating DC current. Okay, later I will talk about this in details. And lastly, is the most important one, a Type B earth leakage relay or Type B RCD is able to react on DC leakage current. This is very important. It's the most crucial points that you must have it in the data centers. Okay, and these are there are 4 types that I've mentioned. So Type AC is the most basic one. You might see it in your house RCCB, like those ELCB or RCCB. Those are very, very common one, Type AC, that we use commonly in the that we use commonly at our home in a residential house. Then Type A is nowadays more used in industrial or commercial buildings. And Type F is not so common. And Type B is the next one that's most comprehensive as most advanced. And it covers all the like alternating currents up to 1000 hertz, and DC leakage current, and DC pulsating currents. Okay, so these are the just a comparison charts. So if you look at If you look at tab B, it has all the ticks. Okay, you look at the last columns. And I think the most important one is these two. Tab B actually can react on DC leakage currents and AC leakage current superimposed with DC. Okay, whereby your other tabs of these RCDs or ELR, it can't react on this DC leakage current. And this DC leakage current is particularly very important because it is very common in those rectifying circuits. Example, UPS, VFD, switch mode power supply. And those equipments are very commonly found in data centers. Okay. Okay. Why data center needs this tab B protection? First thing, these devices actually emits a lot of leakage currents. Example, VFD, switch mode power supply, UPS. And why this device emits this leakage current? Because in this VFD drive or UPS, it has this EMI, EMC filter, or we call noise filter. And this noise filter itself is just a LCR circuits, induct reactor with capacitor circuits. And this particular circuit, it has a common mode and differential modes. And this common mode itself is between line and earth, or line and the ground. That's why it actually contributes to a leakage current. So it is very common for this kind of device to generate leakage current. So it's common. That's why you must know when or how to manage this leakage current in the data center. Because if you let this leakage current flow in the system without doing anything, right, it might cause a lot of hazards. Later I will share with you. Okay, and this is a typical 6 power bridge circuits of UPS or be it a VFD drive. So if you look at the waveform, it's a double hump waveform. It's not AC sinusoidal waveform. So it's actually a double hump waveform. And during a fault or leakage current, you look at the current, it is not the normal AC. That's why if you use a conventional tab AC or tab A RCD or ELR, it cannot pick up this because the device itself, it doesn't react to this waveform. Okay? So that's why you must select a proper device that can react on this waveform. So when there is a fault, there's an fault happen in the system, it can react on it. Okay? So that's why it's so important to have a tab B RCD or ELR. Okay. And how this leakage current is going to affect your data center? First, it will cause nuisance tripping or downtime. Okay, it will cause nuisance tripping and downtime because if the RCD itself, it can't detect, or sometimes it misinterprets the signal. Example, you have a lot of this high frequency leakage current in the system, and inside the RCD, it has the current transformer to measure the current, right? So, and if this RCD itself is not meant for this high frequency leakage current, it might cause the current transformer saturated, and it will give a false signal or false operations. That's why it will cause nuisance trip. Okay. So next, it also can increase the risk of fire. Example, if you have the system has a lot of this DC leakage current, and because the RCD does not react on this DC leakage current, and prolonged DC leakage current in the system may cause fire risk. It may cause fire risk. Okay. Next one, it also will cause hardware degradations or failure because prolonged DC leakage current in the system will cause insulation breakdown. And this sustained leakage current, right, will accelerate the insulation wear and tear, and therefore it will cause hardware degradations. Okay. And lastly, it also will cause risk of electrical short. For instance, if you have leakage current in the system, the ELR doesn't trip or the RC doesn't trip, then you know that this leakage current will cause touch voltage. So if the touch voltage is high enough that when someone touches the panel itself or touch the equipment itself, you will have this you will cause electrical shorts. Okay. And next, advantage of Type B ELR in a data center. First, it can prevent costly downtime or equipment failure and reduce the liability risk. Okay. Second, it can increase or enhance the safety because Type B ELR or RCD can detect all the residue current, be it AC, pulsating DC, or pure DC leakage currents. And it can also prevent electric fires or equipment damage. Okay. And third, it can actually increase the system reliability, reduce nuisance tripping. Example, for instance, or protects against the critical loads, example. And last, for code compliance as well, there are a few codes. We talk about BS, British Standard Code, or IEC Standard Code. Talk about there's some requirement of this Type B ELR or RCD for certain equipments. Example, solar inverter, battery storage system, or EV chargers. Okay. And for applications wise in the data centers, we strongly recommend for UPS system, PDU, HVAC, cooling system, or renewable energy. If let's say you have it in your data centers, example solar inverter or EV chargers, we strongly recommend to use Type B RCD or Type B ELR instead of normal Type A. Yeah. So conclusions. Okay. Type B earth leakage protection release playing a very crucial role in detecting all the form of leakage current in the data centers. So unlike a traditional earth leakage protection relay, so this Type B ensure the protections in modern power environments, making it essential for data center reliability. Yeah, thank you. Yeah, this is the end of my presentations. Yeah. I can't hear you. I can't hear you. I can't hear you. Yeah, I can't hear you. I can't hear you.
Thank you so much for the presentation. Sorry, it's so hard to tell. No.
I can't hear. No, I can't hear. It doesn't work.
Sorry about that, everyone. Now you can hear me. Thank you ever so much for that presentation. Really appreciate it. Are there any questions from our audience? I have a few questions, but is there anything from the floor right now? No? Well, I will kick off with my questions, if that's okay.
Sure, yeah.
So it's very interesting what you're saying. Why can't a standard Type A earth leakage relay protect against all leakage risks in a data center?
Yeah. Okay. Reason being, the Type A is not designed to detect the DC leakage currents. So, and Type B is particularly designed for react on the DC leakage current. That's why in data center, because it has a lot of this DC leakage current, so it is good to have the Type B instead of Type A. For this reason, yeah.
I see. Thank you. And so what happens if a data center uses a Type A earth leakage relay instead of a Type B? Then what's the kind of risk of doing that?
Yeah. So if you use Type A instead of Type B, you might have nuisance tripping in the system. Okay, you might cause downtime. It might also it can't detect the DC leakage current at all, and it causes risk of fire or risk of downtime or hardware degradations, etc. Yeah.
I see. So best avoided. So where exactly should Type B relays be installed in a data center?
Okay, so we strongly recommend to install Type B ELR or RCDs in the UPS system, HVAC cooling system. If let's say you have the EV chargers, you have the battery energy storage system, or you have a solar inverter. So we strongly recommend to have Type B instead of normal Type A RCD or ELR. Yeah.
Okay, I see. And are there any standards mandating Type B in data centers, or is it a recommendation, or what are the current sort of rules?
Okay, currently there are no standards govern about these Type B RCDs in data centers. But however, there are at least two standards govern this Type B. But this is particularly concentrated on solar PV and EV charger. So these two standards actually is BS 7671 and IEC 60364. Yeah. Hello.
Oh, we're back.
Yeah. Okay. Yeah.
Disconcerting. So sorry. And so can Type B and Type A RCDs be used together in the same system?
Yeah, it is possible to use, but you need to do it. You need to coordinate well. You can example. In the main incoming of the panel itself, you can use Type B ELR, and but the outgoing circuit you can use Type A. But then the incoming you must set it with a higher residual current trip point. Then the outgoing must be with a lower set point. So yeah, you have to do some coordinations.
I see.
Definitely you can mix these two Type B and Type A together. Okay.
Makes sense.
Yeah, thanks.
Are there any other questions off the back of that from our audience at all? If not, Our speaker will be available at their stand, which
Yep.
is literally just behind you at
Yep.
stand 31. So please do go and get your questions answered and carry on that conversation. Thank you so much to all of you for joining us, and thank you so
Yeah,
much.
thank you.
for your
Yeah, we also
presentation.
have Type B ELR there, so we can actually demo for you.
Oh,
Yeah.
fantastic.
Yeah, sure.
Yeah.
Feel free to go to our booth.
That's
Yeah,
great.
Thank
See
you.
it in action.
Yeah, thanks.
Thank
Yeah.
you. Are they out of battery or? I don't.
When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool.
working?
Hello, 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 hello. Yeah, can you hear me? Yeah, it's okay.
Hello? Okay, we're on. Okay, perfect. Welcome back to Tech Showcase stage. My name is Audrey Pasquale. I'm the content manager of our APAC portfolio, and it's my pleasure to introduce our next session, which is Tech Showcase with Agreco. on reliable bridging power solutions from build to operation. We have Billy Jury, Global Sector Head of 4 data centers at Greco, on stage with us. And Billy, the stage is all for the next 25 minutes for your presentation. We'll come back at the end to do a little Q&A. So start thinking about your questions, and over to you, Billy.
Okay, thank you. Thank you for the introduction. Hi, everyone. Billy Jury, Global Sector for Data Centers for Greco. I think it will come as no surprise to anyone in this room about the challenges we're facing for power for new build data centers and for expanding data centers. It's not just something that we're seeing across the US and Europe. We're actually starting to see it now across the APAC region as well. So in this session, I'll hope to share with you some of the solutions that we provide to some of our customers who've had delays with grid connection. Some of these are short-term fixes for construction and commissioning, and some of them are going to be for longer-term solutions to help bridging the gap till grid becomes available. Before I go into the context of it, I think I just need to give you a bit of a brief intro into who Greco are, so you know where we actually fit into this space. So we are a temporary means rental, provider of power and temperature control solutions. So that's anything to do with generating power, distributing power, storage of power, testing of power. The temperature control side of it is about keeping anything warm, dry, and for data centers, a lot of the time it's about keeping things cool, okay? Data centers is just one of the sectors that we look after. We've got our fingers into all sorts of pies. Everybody needs some form of power. Most people need, or most manufacturing, most companies need some form of heating or cooling. And we do things like power for events like the Formula One in Singapore. We are truly global. We are based out of the UK. But for this region, we're based in Singapore, Malaysia, Indonesia, India, Japan, Korea, Taiwan, and all over Australia and New Zealand. And globally, we have roughly 10 gigawatts worth of rental fleet. In terms of products, anything to do, like I say, to do with generating power is we're basically looking at generators. So anything from a small 30 kVA up to a 1.5 MVA. We're like Lego. If you need 10 megawatt, we just give you 10 boxes. If you need to step up your voltage to 15 kV, because we generate at 400 volts, we give you another box, which is basically a transformer with, it's got the switch gear and all the protection, everything you need to make it work. We offer a turnkey solution, so we actually do look after the fuel management, and not all our sets they're not just standard diesel sets. We have stage 5, tier 4 final, and gas, and all our sets can run off HVO. Other side of the business is the temperature control. So if you need cooling, so that's chillers, air handling units, cooling towers. Typically, one of our standard workhorses is an 800 kilowatt chiller. If you needed 4 megawatts worth of cooling, we just put 5 chillers together in a central manifold and give you everything you need. Everything we have is all our plant is rent ready, so it's designed to be robust and as emission friendly as possible. So where do we fit into the data center space? There are the 5 main areas: construction, commissioning, once a data center becomes operational, and where we act as the grid, right? So construction phases, that could be just standard site power for construction or for cranes. We supply a lot of dehumidification packages at this stage, mainly so that you're not voiding warranties with your equipment. And we do a lot of comfort, cooling, and heating, so that people aren't taking PPE off when you're building in hot or cold areas. Commissioning, everything electrical, everything mechanical inside a data center needs to be tested. We have the solutions to be able to provide the fictitious loads you need to be able to do that, including now with what we're starting to see with AI, starting to look at some of the liquid cooling stuff. Operational sites, we do a lot of upgrade refurbishment type work. So if you've got a UPS that's reached end of life, you may want to look to swap that over. You've still got to keep your data center alive. So we supply components to allow you to keep the lights on while you're doing all your upgrades. Another area comes in from the operational side is emergency. So let's say you've got a chiller and a compressor blows at 2 o'clock in the morning. Who you're going to call? You know, the fact is we've got quite a large fleet spread across the world, ready to support these emergency type situations as well. And then we're kind of the last area is where we're actors grid, but I'm going into a bit more detail about that. Temporary power gets used a lot for construction, and our customers have made some bold statements about reducing the amount of carbon and the emissions that they're looking to put in there. At Greco also have set ourselves some goals. So we're aiming to be net zero emissions in our facilities and our operations by 2035. So that's introducing EV vehicles and all that sort of stuff. But we're also looking to reduce the emission intensity of our energy solutions by 30% by 2030. So that means our product mix is starting to change. It's not just generators. We're now looking at battery storage. We have UPSs. Most of the new generators that we're bringing online now are all stage 5, tier 4 final. Investing a lot more in transformation. Also being able to supply alternative fuels such as gas, HVO. And all of our gas generators are actually already 20% hydrogen ready. For longer term solutions, we have another part of the business called Agreco IPP, where we're starting to look at solar, wind, battery storage, and a bit of thermal. These are going to be 15 to 20-year deals. So you'll see more about that over the coming years. So trying to bring some of these greener solutions in, even though it's temporary power at construction stages. You can see here on this presentation here, we've got this is actually power for a cabin complex. It's for one of the hyperscalers in Denmark. And initially they just wanted 1 megawatts worth of power, and they were going to use one large generator to put that in. Generators in general, you're only probably going to run somewhere near its maximum for 5% of the actual time. So this particular customer, we convinced them to put in a load on demand system, which means putting in 3 smaller units designed to run as the load goes up, one generator turns on and another turns on. As the load drops, it turns off. So you're basically only using the fuel that you need to produce the kilowatts that you're looking at. Agreco also has something called ARM, which is Agreco Remote Monitoring. There's 2 benefits, or 2 main benefits to this. One is it allows us to catch faults before they happen. Let's say a generator is going to run out of fuel or something like that. We can catch that before it happens. But it also lets us see the load profile, right? So the fact that we can see the load profile for this particular customer warranted itself to basically put in a battery, right? So what we have here, see where it says greener solutions, the box there, is a 500 kilowatt 1 hour battery. And that battery actually runs the show most of the time, okay? And basically the generators are designed to run at 70-80% load to charge the battery back up, so you're getting the most kilowatts out for the litre of fuel you're going to put into that system. Other benefit to a battery is obviously there's no noise, so at night you're going to keep residents around you much happier. And this particular system, the solution we put in here, you can see on the left-hand side, that's what you would have been getting if you had a 1 megawatt engine on its own. The middle column is the savings that we accrued. So, and there's roughly a 60% saving on the amount of fuel they burned, therefore the emissions they were putting out, therefore the cost of fuel. Power doesn't all necessarily just have to be about generation, and even at construction stage. And this particular package, or the photo you can see here, is a data center where they had delays with construction, which impacts the commissioning, which then impacts on the networking time. So when the network guys want to get in and do what the magic they have to work on their servers. So for this particular solution here, to speed up or help these guys get back on track, we put in a temporary UPS backed up with generators, and it allowed them to liven up their servers while the construction, the commissioning team will turn the lights on and off around the actual data center. We see a lot, or we have a lot of inquiries and a lot of solutions that we've actually delivered for commissioning power. The loads tend to be a lot more lumpy. So, you might want, if you were commissioning a 50 megawatt data center, you might have 5 megawatts on, then you might have 45 megawatts on. The loads can be very, very jumpy. So for those types of applications, you're better suited to diesel generators or diesel generators that can operate on HVO. Basically what happens here is we generate the power, we transformate the power up to whatever voltage we need to go, we connect into the substation, and to all intents and purposes, the building is seeing, or is effectively seeing what it sees as the grid, so you can actually carry out what you need to do in terms of your commissioning. This picture here is actually a project that we've done recently in Malaysia. It's a 10 megawatt at 20 kV package. We are doing a 60 megawatt package at 34.5 kV for one of the hyperscalers in the US. And there's a lot more of this that's in the pipeline, especially across the US, and everything that's starting in the US and Europe is going to filter across the rest of the world. So, in terms of a case study, this particular package here is where we're bridging the energy gap. Okay, so one of our customers, it was a colo provider that was housing one of the hyperscalers in there, needed 14 megawatts worth of generation, and they needed it for 18 months. Now, luckily for these guys, there was actually mains gas available in the area. So the package here is actually gas generators. All we need to be able to make something like this work is a flat area. So basically some compressed gravel. You can see that the boxes are all in 20-foot containers. A Greco loves a 20-foot container. Very easy for us to move around the world. Very easy for us to implement. And like I said, it's like Lego. We can build it up and take it down as needed. This actual package, there was 12 generators, 10 running, 1 spinning, and 1 true spare. And we also had a 1 megawatt, 1 hour battery on this package as well. And this was the battery, although it gives you a bit of spin in reserve, gas generators they're not as tolerant as diesels when you put large load steps on and off. So the battery helps smooth that out. Sound is always an issue with these types of installations. I mean, the generator, without any of its sound attenuation built into it, it's about 85 dB at a meter. With the localized sound attenuation, that gets us down to 75 dB at a meter. And then you can see around the outskirts of the compound, there's more sound attenuation. Where that white van is, we're actually at 55 dB. So pretty quiet, because there was an off-taker over here somewhere. Sorry, a resident over here somewhere where we had to make sure that we're keeping the noise down. This is effectively a mini power station. So it's manned 24/7. Like I said, it's only meant to be on for 18 months. It actually was on for 5 years. All right. So we've done this for all the hyperscalers. I know sometimes customers are a little bit nervous about looking at using fossil fuels as a way to bridge the gap, but with the pressures that's out there, we know that this solution works, and we know that the hyperscalers will take it on. That's what 50 megawatt looks like. This is actually a 5-year deployment. Because this was over a 50 megawatt thermal in terms of the amount of gas it was going to use, there's a third box on there which is SCR, so that reduces our CO2 and our NOx further, and allows us to comply with the needs of the local legislation to actually implement this design. It's not all about generation. We also have some large-scale transformation. I mean, this one here is actually a 125 MVA, 35 up to 256 kV package. Across the APAC region, typically we have up to 20 kV, some 33 kV in a 20-foot container, roughly around about 6 MVA. But we don't have a lot of this equipment, but we do have it. So if there are any needs for temporary substations or anything like that, give us a shout because we may have something to help you out. So, as a bit of a conclusion, if speed is the key, there are options available. With all the like I said, all the hyperscalers have already directly used these solutions or via their lease partners. And the discussions we're having now, especially in the US at the minute, there's a lot of customers talking up to 200 megawatts worth of grid bridging solutions required. And I touched on earlier about Agreco having Agreco IPP, so we actually do have some longer term plays also. So grid supplies are no longer guaranteed without delays. What I've just gone through in the presentation, it obviously impacts stuff that's going on with your construction and your commissioning. There are solutions out there, and one of the great things about our solution is we can ramp up and ramp down with your actual load profile. So you're only paying for what you actually need. And that is the end of my presentation.
Perfect. Thank you very much, Billy. Okay, we do have a little bit of time for Q&A. So if anyone in the audience has got a question, please raise your hand and we'll bring a mic to you.
No tricky ones, though.
I've got a couple of questions for you, Billy, to get us started. So my first question I have here is, why do data center developers rely on temporary power? Why not wait for the grid?
Mainly it's a speed thing. So, they want to build in a certain area. They've got customers that they've got lined up already. It is a lot of the time it is a temporary fix. It could be 18 months to 5 years, but basically it enables speed for them to be actually build when and where they want to.
Thank you. If anyone's got any questions, please raise your hand and we'll bring a mic to you. I've got another question for you, Billy. Are there any greener bridging solutions available?
So, burning fossil fuels obviously is probably frowned upon in terms of being a green solution. But the fact that we can fit SCR and all these sort of things onto our packages, that helps reduce the CO2. But some of the stuff we're now looking at with Agreco IPP, so we're now looking at potentially building solar farms, building wind farms, putting battery storage in, and a bit of thermal, and acting as grid. It's a much longer term play, but that's a much greener solution.
Thank you. Why not use turbine instead of recip engines?
So turbines have their place, and we are, as a company, looking to purchase turbines ourselves, especially for base loads and what have you. For shorter term durations, installing recips is quite quick to do. That's one part of it, but it is the efficiency. If something's going to go on for a year, our equipment, the recip engines that we've got, and we basically go out to look at everything, are probably about 5% more efficient than turbines. And over a year, if you've got 10, 50, 100 megawatts worth of power, the cost savings associated with that 5% is massive.
Perfect. Thank you very much. I've got one last question for you before we wrap up. And my question is, what if gas mains is not available?
So, good question. So in the US, we bump into this quite a lot. And what we can supply is virtual pipeline, which means we can actually truck in CNG or LNG. It's coming in either a liquid or a compressed gas format. We actually do have gasification systems, so we can actually turn that liquid or whatever it is into a gas, and we can burn it there and then.
Perfect. And my last question to you, Allied, is where can we find you on the show floor if people want to carry the conversation with you?
We are just over there, just behind number 29. I don't know what number are we, John? What's our stand number?
Stand number 28.
28. There you are. No, stand 28 if you want to come and see us.
Perfect. Thank you very much, Billy.
Thank you.
Oh, we've got one question. Let's go for it.
Okay, thank you, Billy, for the presentation. My name is Sandy. I'm from Equinix, Indonesia. So I have one question for you. So can you simulate what kind of the failure scenarios that resistive and corrective probably can give the example.
So the design of our system, right, when we put them in, is as good as grid or better, right? So the solution we put into Ireland, I think it was 98% uptime was the actual requirement. We were something like 99.2, something like that in terms of the resilience of our system. But at rack level, with your own UPSs and your own standby generators, you're at the 5.9s and the 6.9s, however you guys operate. Thank you.
Perfect. Any other questions? Okay, I think we can wrap this up. Thank you very much,
Okay,
Billy, and
thank you very much.
for listening
Cheers,
in.
guys. Thank you.
Okay. Good afternoon and welcome back to our Tech Showcase stage. My name is Audrey Pasquale. I'm the content manager for our APAC portfolio of events, and it's my pleasure to be introducing the next session, which is a market showcase from DCD. They're going to talk to us about inside Asia-Pacific data center boom, how Southeast Asia compares to Northeast Asia and Australia and New Zealand. It's my pleasure to welcome on stage James Murphy, Vivian Wong, and Jing Wen from DCD.
So we stick them on, right? Thank you everyone for joining us here today. As you can see from the screen today, what we're going to be going through is we're basically going to be doing a run through on how Southeast Asia is comparing to some of the other hotspots in the region. In this particular case, we're going to be focusing on Northeast Asia. And when we talk about Northeast Asia, the focus is really going to be on Japan and Korea. And then ANZ, which is really going to be neat. Have I gone? Okay, yeah, great. Very quickly, here we are. So I see some friendly faces in the audience. Nice to see you. Thanks for. But we're a data center. Okay, hopefully now people can hear me. Yeah, we're a data center market intelligence provider, headquartered in the UK, but you've got myself, Jingwen, and Vivian, who are part of the Singaporean team. Sorry. Team of analysts all over the world, speaking loads of different languages. That's how we get our insights. So just very quickly before we start the session, I'm just going to go through our supply definitions, because I think everyone has a slightly different definition of what constitutes live supply, what's under construction, committed, early stage, etc. So I think live IT is fairly self-explanatory, anything that can support IT. Under construction is very, very precise. We use a very precise definition. So we only regard a facility as under construction when the M&E equipment is installed and the white spaces can support IT or is on the process of being supporting IT. So, for example, a shovel in the ground to start powered shell, we would not regard that as an under construction facility. That would fall into the next stage, which is committed. So in this instance, committed essentially means committed to the project. So all of the necessary elements are in place: land, power, water, permitting, whatever it might be. And then the final stage is early stage. So this might be where someone's made a big announcement, particularly like a campus-style development of, let's say, 500 megawatts, but we haven't seen evidence yet that they've secured all the power. They may not have water, may not have planning permission, may require a significant anchor tenant. So that will fall under early stage. So it's possible that one facility would have capacity in all 4 different stages, especially a campus-style development. But just so you're kind of have a sense of what these are. So all 4 is total supply, live, under construction, committed is what we would consider qualified. And then under construction and committed is kind of like immediate or short to medium term pipeline. So very quickly, just to give the global perspective before we zoom in. So this is as of Q4 2024. So we're using a snapshot in time here just to kind of keep things consistent. As you can see, we're tracking 138 megawatts as of the end of last year in the Americas. Majority of this is obviously in the US. EMEA, about 36 megawatts, the most probably constrained region. And then APAC, we're over 50 gigawatts now, 51.9. I actually logged on today and had a look at the US. And the US alone is up to 150 gigawatts. So in the space of kind of 6 months, they've added an additional 15 or so gigawatts to pipeline there. So like a lot still happening. In terms of live IT, so now we're just looking back at live. So again, this is where the definitions become kind of important to be familiar with. In the 5-year period, the CAGR for Americas and APAC, as you can see, is just under 20% for these 2 regions. EMEA, again, because of the kind of the well-documented constraints, is slightly lower, but is still pretty healthy, 13.3%. In terms of the actual growth, or the live IT, as you can see, again, for Americas, leading the way, again, most of this in the US, nearly 14 gigawatts, about 5 in EMEA, and coming up to 8 in APAC as well. So just showing this because live IT is growing, but I think the pipeline is what's really significant in all these markets, and that's obviously additional cloud compute coming on, as well as obviously AI, which we're only just kind of seeing the very start of. So with that, I'm going to pass over to Vivian. So Vivian's going to give the Southeast Asia kind of snapshot and just kind of introduce some of the key markets across APAC.
Like this. Thank you, James. So let's start off with Southeast Asia, one of the most dynamic region within APAC. So to give a bit of context and also set the ground for discussion, I have included the total supply by Southeast Asia metro. So you can see from Johor to Hanoi. So all of this capacity here includes live, under construction, committed and early stage. So that's why the figures that you're seeing is relatively large. But the purple bars refers to the live IT capacity. So there are a few broad trends that we wanted to highlight here. So first would be the Sejori market. So if you look at Johor and Batam in this graph, you see that these two markets are the fastest growing, which average a CAGR of 212% for Johor and 298% for the Batam market. So both of these markets actually grew out of the spillover from Singapore in the early days. But subsequently, we are also seeing that these two markets are maturing and offering some of the unique characteristics that the markets can actually offer to serve regional workloads. So they are also evolving as independent markets, which we are anticipating to see in the few years to come. Second would be for the Bangkok market. We are seeing that the total supply now is following Johor, the second biggest market within Southeast Asia. So previously it had experienced a false start, but now we are seeing a lot of interest from investors, as you can see from the early stage IT capacity. A lot of this is from the large landside acquisitions by developers who are interested to build data center campuses within the EEC. So there will be a spotlight on Bangkok later, so there will be more details given. And third would be on the more nascent markets like Ho Chi Minh, Manila, Hanoi. So all of these markets are currently seeing a bit more of the supply side activities. Smaller deals in the markets by the cloud service providers, but they are present in the market. So we are anticipating that it will take the next few years for the markets to mature and clear up some of the bottlenecks. Like in the case of Vietnam, I think licensing and getting the regulatory approval is a challenge for a lot of international operators at the moment. Okay, so the first market spotlight would be on Malaysia. So this, the whole of Malaysia actually currently hosts about 6.4 gigawatts of capacity. 70% is actually now concentrated in Johor. So you can see that very quickly, since the emergence, Johor has eclipsed KL, which now only makes up about 27% of the market share. And 3% is spread across markets like Penang and Sarawak, with still very limited activities at the moment. And this shows the IT megawatt in terms of live supply and take-up. So there are a few milestones that we wanted to highlight here. So 2021 was the turning point for Johor, where it first saw the first build-to-suit project by Microsoft come live in the space. And 2022 was the entry of ByteDance that contributed to about 200 over megawatts of co-location take-up that really allowed the market to accelerate. In 2023, 2024, we started to see a lot more diversity in the demand. So apart from ByteDance, there's also the regional tech companies like C Group, Alibaba, NVIDIA Cloud Partners are all entering the space. Microsoft has also started their land acquisition process. So now we are seeing about a total of 4 plots, which can account about 600 megawatts in the market. And as for the occupancy take-up, you can also see that from 2022, it has crossed over to 89%. This is also reflective of Johor as a build-to-suit market, where the pre-lease tend to exceed the current existing live capacity in the market. So then this is the chart for Greater KL. So we can see that for KL, the supply and demand dynamics is a bit more stable growth, where on average, like the market is growing about 10 to 20 megawatts and 30 in some years. But there's expected to see a shift in this demand. There will be more live capacity added because as of end of 2024 and start of this year, a lot of the Western hyperscalers started to start construction on their self-built projects, in which we are seeing that all these self-built projects contribute to 30% of the market composition, which is also the biggest share within all of the Southeast Asian countries. So this also reflects that among the Southeast Asian countries, the Western hyperscalers are also planning Malaysia as one of their main base for some of the bigger workloads. The next market spotlight would be Thailand. So as mentioned, there previously was a bit of false start, but since last year, we started to see a lot of projects moving towards the under construction and committed category. Among the activities clusters such as Samut Prakan, Bangna, Pathum Thani, I think EEC is still the most popular, given that it has relatively lower flood risk. I think it's a common challenge among the Thai market. So it stands at about 2.4 gigawatt. And one item that we wanted to highlight here would be AI's growing share of DC capacity. So this is unique to Thailand at the moment, where since Q1 of 2024, so I filtered this by quarter instead of years because it just only emerged in the past few quarters. So it's led by Siam AI, which has started to do co-location capacity across various data center operators. So as of the latest quarter, we're seeing that AI take-up makes up about 27% of the Thai market. Then Indonesia is more of an interest market because it was one of the first few Southeast Asian countries to take off as a data center location. But in the recent few quarters or years, we have been hearing that how's the market doing? It seems to have lesser activities currently. So I think the market is still growing, but in a more stable form. So the market has about 1.8 gigawatts in total. Jakarta is still the primary market with 75% of the capacity. Batam accounts for about 22%, but this is expected to start to see a change in the proportion because Batam also first saw its first hyperscale contract in the market as of second half of 2024, and the facility associated with this contract has just recently came live. So you see that this actually overflipped the whole occupancy rate to 72%. Yeah. And on this note, we also noted from NVIDIA that Oracle currently has reviewed plans of 260 megawatt for the Indonesian market, which Batam seems like the most likely destination to be for this capacity. And this is the chart for Greater Jakarta. So as you can see, the market is averaging a bit more stable growth, 20 to 30 megawatts of average take-up. So I think now has also seen a bit of interest towards even the third market. So I think there are some discussions around markets like Surabaya, where some of the operators have already started construction, so I think more announcements are expected to come. So just to wrap up with the opportunities and challenges, so I think cloud and AI demand is still expected to drive the next wave of growth in Southeast Asia. Cloud was expected to be more of the backbone, where some of the local demographics, like in the case of Indonesia, where the population is very large and a significant proportion of them under the age of 30, this will contribute to increased demand for digital tools and hence digital infrastructure. And because for Southeast Asia, it's known to be a cost-friendly destination for data center development, so it makes sense for AI deployments, which is in significant, large scale. So in this aspect, I think it has been a pretty favorite destination, so you might see this proportion continuing to increase. Adoption of emerging technologies. So 5 years back, we wouldn't expect Johor to be a location for very sophisticated GPUs like the Blackwell that is going into the YTR Green Data Center Park. But now he has started the fit-up process. So we are also seeing the adoption of more advanced cooling technologies like direct-to-chip cooling. And on the construction side, we are also seeing new approaches such as the modular prefabrication. So all of this would also contribute to the knowledge diffusion among the local players. And also some of the exhibitors here have also shared that they are building a plant in Malaysia for prefabrication. So this also allows the local supply chain to grow. And green energy opportunities, I think so far for Southeast Asia, there has been quite a bit of potential and different aspects. So there's solar in Malaysia, hydro in Vietnam and Thailand, and there is also geothermal discussed in Indonesia and also Philippines. So far, Malaysia is one that the authorities have launched the initiatives that allow the private sector to participate. So there was the corporate green power purchase. So this is a virtual PPA that the data center operators can offtake from solar farms within Malaysia. So AirTrunk and Day1 were among the first few to offtake from the first pilot run. Then there is the corporate renewable energy supply scheme. So this allows private renewable energy player to participate via open grid access. But I think the challenge that comes with it is the high access charges. So I think all these frameworks are still being reviewed to see how renewable energy can be a viable option and not just a premium alternative that people can undertake. And as for challenges, I think so far, because for Johor, it has grown at a pace that nobody has expected, even the government when expanding the digital infrastructure. There has been a short-run crunch, especially in popular areas for power and water. So moving forward, I think we're seeing some of the operators move out into areas that are under, that has previously not seen any development, so not tested per se. So they're really doing the groundwork from scratch. It could be a plantation that they're starting the development of from. So I think communication from the government on relevant timelines will be very important. And geopolitics, I think Southeast Asia has been relatively affected by both the Diffusion Act and also the recent tariffs. So I think a lot more building resilience among the operators and investors and to respond in times is very important. And the last point would be on sustainable industry development, both an opportunity and challenges would be to see how we can incorporate the best practices when scaling up digital infrastructure in Southeast Asia to ensure that it's for the long term and not only to fit the current existing demand. So with this, I'll hand over the time to Jingwen, which will go through Northeast.
Okay, hi everyone. Fingers crossed you guys can hear me because I don't have the headphones on. Just like I have my fingers crossed that I'll be able to fly out tomorrow, but we'll see. So Northeast Asia. Before I start, I think I'll introduce myself first. I'm Jingwen. I'm the APAC Research Manager. I'm also the analyst covering Japan and Korea. So same thing you're looking at here. I think you're looking at, the markets, the metro markets in Northeast Asia. So Japan, Korea, Taiwan, Hong Kong, the breakdown across the 4 supply categories that we track, as well as the 5-year CAGR of total supply, which you see in red above all of the bars. 30 to 40% across a lot of the markets, pretty good numbers. I know they look very small compared to Southeast Asia, which we saw above 100%, 200% just now, but pretty healthy growth. I think Hong Kong stands out probably to everyone here because 10%, kind of low compared to everyone else, but this is going to be mainly because of geopolitics, which has affected the market since the beginning of this period that you're looking at the CAGR for. The rest of the markets, like I mentioned, pretty good. The 2 markets that we will be spotlighting today, pardon me if I'm going quickly because we're a little bit short on time, will be Tokyo and Seoul. So to start with Japan first, if you look at the number in the middle, 6.7 gigawatts. At current time, I think we've been overtaken by Malaysia. So we're probably about 5th in APAC right now, behind China, India, Australia, Malaysia, and then Japan. 72% of that is in the greater Tokyo area. We do expect this to decrease because there has been some growing interest into Osaka, as well as further out markets like Kyushu and Hokkaido. So one thing I think I'd like you guys to keep in mind, so that will come into comparison later when we look at Korea, which is the amount of light pink here, about 1/3. So early stage supply, the reason why we like to talk about early stage supply is because it's kind of a proxy for 2 things. Usually in developed markets, it's a proxy for market challenges, and the developing markets is usually a proxy for interest, investment, and speculative builds. So Japan, not bad. Tokyo, you're looking here at the live IT supply growth and live take-up growth, as well as the occupancy rates on the line above. So to put it into context, in other markets where there's typically a better balance between supply and demand, you're looking at an occupancy rate of 80 to 90%. So Tokyo has hovered above 90% since 2021. And the market is currently facing a bit of a short to medium term undersupply situation. This is really coming from a very Japan-specific constraint, which is the constraint around general contractor and subcontractor resources in the country. Obviously, also power and land are a big factor, but in a lot of cases as well, GC timelines tend to be the one that introduces a lot of delays into development periods and delivery of supply into Japan. So very long delivery timelines, which is contributing to the undersupply situation in the market for now. Korea, so 6 gigawatts. This is where you put the comparison for the light pink. I'm not going to walk there so you guys can take your photos, but you can see that the light pink in the donut chart on the right is a pretty big proportion of the supply. So a lot of early stage supply, which is really inflating the numbers for Korea. If you kind of combine that with the 2 pie charts on the left, which you don't need to scrutinize it, I'll tell you what it's telling you. It's basically saying that a lot of the early stage supply is concentrated in outside of the greater Seoul area. So everywhere to the south of the country, past, kind of like the Yongin, Ansan area. A lot of the early stage supply there is coming from very big 100 megawatt, 300 megawatt, 1 gigawatt announcements of campuses from developers that don't necessarily have a track record in the industry, not just in Korea, but generally across the whole of APAC and even globally. So a lot of this early stage supply, so about 4.3 gigawatts as you can see there. I know the number's really small probably from your standpoint, but 4.3. A big proportion of this is probably not going to be considered as real supply. So it's likely that a big part of this is not going to actually be delivered in the end. So the actual size of Korea is actually a lot smaller than the 6 gigawatt number that you're seeing here. So for Seoul, same thing. Again, it's a live supply growth, live take-up growth, as well as the occupancy rate on the top. As you can see here, the occupancy rates are a little higher than what Tokyo is observing. So about 96, 97% over the past 3 years from 2022 to 2024. And the reason for that is, again, actually a very Korea-specific issue, in the context of APAC at least, is a lot of civil complaints around a lot of developments across the Greater Seoul area, at least for the established clusters in the Greater Seoul area. So Seoul, Incheon, Gyeonggi area being Yongin, Anyang, and then north in Koyang. So a lot of projects face a lot of difficulties with delivering supply because civil protests, petitions, and then that gets escalated into local governments, that basically they stand behind the people because they want to get votes, especially when it comes around like election times. And that is introducing a lot of difficulty for a lot of developers in the Greater Seoul area. So a very, very strong undersupply situation, much more so than Tokyo is facing at the moment. To wrap it up with the opportunities and challenges, I did talk about a few of this throughout the, spotlights, I guess, on Tokyo and Seoul. The one thing I think that kind of wraps up the section really is going to be a little bit more maybe applicable to Japan and Korea. I'm a little bit biased because I cover Japan and Korea, but these markets are very constrained, which also means that, if you are able to enter the market, there's definitely some benefits to be reaped. It's just that it's really difficult to enter. To talk about Taiwan a little bit, because I didn't really talk about this market for this bucket of markets in Northeast Asia. There's been a lot of, well, not a lot, but there has been growing interest, growing activity, both supply and demand from both, obviously the operators, the developers, as well as the hyperscalers into Taipei, as well as kind of south, but the south has been there for a while. For Taipei, there have been a few regulatory changes last year, which might signal a little bit of concern or a growing concern that regulations might be a little bit more difficult to navigate, especially in the kind of like Taoyuan area, which is kind of like northwest of Taipei. So very, very briefly, that was Taipei and Taiwan. I'll pass the time back to James now to talk about ANZ and wrap up the session for us.
Thank you, Jingwen. So, well, according to the clock here, 3 minutes and 30 seconds to do Australia. So I will be very, very quick. Australia, New Zealand. So focusing on Sydney and Melbourne because this is really where all the action is happening in Australia, like Brisbane, Perth, Adelaide. There are facilities in some of those markets, but they're generally sub about 50 megawatts or so very, very local. It's really where Sydney and Melbourne is at. Sydney is kind of the historic, I suppose, home for data center capacity in Australia, and Melbourne is a bit like Osaka to Tokyo in the Australian context. This is the really growing market, and we're going to talk about this a bit more in a sec. Canberra's got historic workloads, government, AWS, or not, Azure have got a cloud region there as well, again, generally serving government stuff. But like I said, in the Australia context, it's really Sydney and Melbourne, as you can see from the CAGR numbers here, both growing at a pretty healthy clip and have been for the last 5 or so years. Auckland as well, again, very healthy CAGR numbers here, over 70%, but growing from a very, very low base. So New Zealand is kind of a market to kind of keep an eye on, but at the moment there is, even with Microsoft and AWS moving in, the market is still relatively slow, and most of the capacity there is being serving a domestic audience. Looking at Sydney, so as I mentioned, Sydney is the market which has seen the vast majority of Australia's capacity historically, growing over 20%. In terms of live supply for the last 5 years. Occupancy has always been pretty high. A couple of years ago, it was starting to get into slightly worrying territory, getting close enough to 80%, but since then it's actually risen. Always get asked, is Sydney oversupplied market? And I think people have been thinking that for probably the last decade, but they do always seem to absorb the capacity, and it seems to be the market in APAC where people are just consistently happy to continue deploying. So, like I said, pretty significant growth over the last couple of years, and also an increasing occupancy as well, which I think points to kind of the health and the buoyancy of the market. Melbourne. So this is a really interesting one because Melbourne, as you can see here, has got a huge chunk of pink, which, as Jingwen and Vivian touched on, this is the early supply. So a lot of people are now looking at Melbourne. Reason they're looking at Melbourne is because if you look at the right, you'll see this is a new chart, the first time we've seen it, but you can see that a big chunk of this market now is AI. So Melbourne, I think, is probably the first, or certainly one of the first markets in APAC where you're seeing significant AI deployments. And if you kind of compare Melbourne and Sydney, who have got increasingly comparable capacities, you'll kind of see that Sydney is getting a lot of the cloud capacity for Australia, and Melbourne is taking a lot of the AI. So really, really interesting dynamic. A lot of big new projects coming up here. And in most cases, these projects are serving AI workloads as well as cloud, but a lot of them are purely AI now, which is pretty interesting in the APAC perspective because it's really the first place where this is happening. Australia challenges, cloud and AI demand is strong. Like I said, cloud is strong in Sydney, AI in Melbourne. It's Western friendly, so I think any kind of US workloads or US firms they're happy working in Australia for a variety of reasons. International connectivity, like Sydney has been a hub for 10 plus years now, and that goes along with a lot of subsea cables and everything else. People are just comfortable in Australia, basically. Challenges, so the question of Chinese workloads or any sort of Chinese involvement creates issues, and only in the last couple of days heard of quite a interesting case of a firm not being allowed to develop in Australia, so that it continues to linger on in the background. The approval process can be long and tricky. So Australia's got one of the most transparent planning processes. If you go into the New South Wales website, you can see any sort of DC development. A lot of the operators do try and hide them and give them fancy code names and stuff like that, but anyone can log on. Once they know how to navigate the system, can find that. That's good and bad. Good for us, makes our job slightly easier, but it means that civil complaints can come in and they can stop a lot of projects. So that's a increasingly a big issue in Australia. And then power constraints. So certain AZs in particular have got power constraints. So Sydney North, kind of the Macquarie Park area, that's where AWS and Microsoft both have AZs. That's a very power constrained market. So some of the cluster or some of the region or some of the AZs, I should say, are power constrained, which obviously creates issues, particularly for ones who are dependent on that architecture. Very quickly, just to wrap up. So in the APAC context, as I mentioned, Southeast Asia plus S, that S stands for Singapore. So last 5 years, both of these markets have grown over 20%, so very, very healthy growth. Northeast Asia, which, as Jingwen mentioned, we're talking about Japan, Korea, Taiwan, Hong Kong here, growing at a smaller CAGR, again, mainly due to the kind of well-documented constraints, particularly in the biggest markets, Seoul and Tokyo, but still pretty significant amount of live IT added across all markets, 1.4, 1.3, and 0.8 respectively. So all of the markets are growing. They all have different challenges, but growing for different reasons. Again, looking at it in terms of the overall picture, so just the previous slide was just looking at live supply. We're now looking at total supply. So as you can see, when you factor in the pipeline as well as this, you can actually see that Southeast Asia now is the biggest pipeline of projects. So that's, to Vivian's point, that's because of markets like Thailand now all of a sudden, Johor. These markets have big pipelines because generally speaking, it's easier to get big projects built in these new markets, or that seems to be the case moving forward. Pretty big pipeline across all of the different markets. So that's us. We're out of time. I don't believe we have any time for questions, but if anyone does want to ask any, myself or any of the team questions, we will be around. We actually do also have a booth over there. Please feel free to reach out to any of us. So I'm kind of looking over the whole of APAC, Jingwen, Northeast Asia, Vivian, Southeast Asia, and then we've got a couple of other analysts who are not with us today back in Singapore, that they can answer questions around India, around Australia, around some of the other markets across the region as well. So please feel free to reach out. All very active on LinkedIn, all that kind of stuff. So grab us, email, LinkedIn. If you want to come shake our hand as well, we'll be around. We'll be at the booth over there. So yeah, that's it. Hope that was useful. Sorry, I had to go through things very, very quickly, but I hope that gave a kind of a good snapshot and a good comparison between the different kind of some of the different regions across APAC. Thanks, everyone.
Thanks, James, Vivian, and Jingwen for this presentation. If you want to find them, they're on the show floor at stand 50. We've got another presentation coming after this, so please stay with us for a presentation from Huawei. Thank you. Testing. Okay, there we go. Good afternoon and welcome back to the Tech Showcase stage. My name is Audrey Pasquale. I'm the content manager for our APAC portfolio of events, and it's my pleasure to introduce the next session. We are here with Huawei today for a tech showcase on building a robust foundation for intelligent computing era. I would like to welcome to the stage Fu Fangyong, who's the president of Data Center Facility and Critical Power Business APAC at Huawei, and he will be giving us a presentation for the next 25 minutes. Over to you.
All right, thank you, Audrey. A very good afternoon. Thank you very much for staying back to listen to us. My name is Fang Yong, and today I would like to share a little bit with you on Huawei vision of what it takes to build a robust foundation, for intelligent computing era, especially the AI DC. Okay, so I think I don't think I need to spend a lot of time on this slide, but what I'm trying to say over here is over in the past 2 years, AI has actually really reshaping the whole industry. The IT, the AI, the development, the investment, as well as how we will build the data center. So if we can see over here, what we can see is the investment, right, for AI infrastructure. Over in the past few years, is already exceeded, more than 300 billion US dollar. And its compound annual growth rate, is actually, almost 33%, which is actually a lot higher, if we compare that, to the golden age of internet, which is, about 25%. So, and then we can also see that the demand, for talents over in AI industry is actually increasing every year, at almost 30%. So what we are trying to say, what we are seeing over here is AI is no longer a hype. Yeah, and as a matter of fact, is a systematic industry revolution, that's actually taking shape and is happening. And okay, so when we're looking into what is happening over in the AI industry, so we can also see that just over in the span of 2-3 years, there is many unexpected development and advancement over in this industry. So the first development that's beyond our expectation is the large language model development expectation. So we can see that in the span or only 2 years, we can see the model capability has increased so much that from imitating a human decision to actually be almost 90%, of what human can do actually in certain industry, in certain areas, right? For reasoning, and also especially coding, right? And also we can also see that DeepSeek, earlier, when they launched earlier this year, they actually re-engineer how you train the model and to bring down the cost, by almost 90%, of what you need in order to train a large language model. And the next thing that we can also see that is how the computing capability is advancing, surpassing our expectation, right? Today we can see that the inference capability is like almost 30%, more than what we actually be able to do a year ago. And training performance is actually fourfold, right? So with the latest chipset development, advancement, etc. So this industry is really progressing very fast, and hence we can also see that why the construction of AIDC, a huge data center, has actually surpasses our expectation. We used to live in a world where spending millions away in data center is a norm. But today we can see that $1 billion of investment going into AI data center, and AI data center construction has become a serious traction for a lot of major funds globally. And all these, again, is also, charging and accelerating what we see, as an industry, revolution over in the AI. And when we are talking about AI DC, so we are not talking about a DC that actually conventionally what we have seen. So then coming back to AI DC, what exactly is AI DC by context? So from our perspective, AI DC actually is a DC that in majority is actually run by from CPU to GPU, right? From asynchronous processing to synchronous processing. And how this single computing unit, has actually evolved, from a conventional DC to an AI DC is we used to see a server unit, and today, in AI DC, we're talking about supernode, we are talking about cluster, right? Clustering, of the system. So it's no longer a server-based, computing capability. And then we can also see that, the chipset, the fast iteration of chipset performance is almost every year. So we can seeing that these three characteristics actually construct, what we actually see as a AIDC. So from AIDC, we can see that we used to take for example H100, right? You can say, in one server is actually 8 GPU. You put in the rack 4 server, you have 32 GPU, and then they form a supernode, right? And then from a supernode, you will basically use it to form multiple cluster of supernode according to your needs, whether it's going to be inference, whether it's going to be a training model, and etc. So supernode has actually become a basic unit, driving key indicator improvement. And then in order to maximize the computing power, of AI DC, so it requires a triple balance, from where we, from what we see in terms of building the AI DC. The first is scale, right? So when we're talking about a unit computing power cost, so we can actually see that a 10,000 GPU cluster is actually a lot more efficient than a 1,000 GPU cluster. So that's the reason why you can see that a lot of AI DC start, from jumping from 10 megawatt to 50, 100, 200, and etc. Because that gives you the maximum return of every unit of power that you are investing into your DC, right? And then the second thing is about when you are running all these, among different cabinets, and racks and etc. You have actually, the loading, that it will actually compute, actually consume a lot of power, and so how you actually making sure that this power, is sustainable and is actually maximizing, to how you'll be able to run your supernode. That's actually another important consideration, for building an AI-DC. And lastly, when we are building a supernode, as what I actually shown just now, a supernode is consisted of many racks and supernodes. So the other cost that we have to take into consideration is connectivity, right? And connectivity is a huge cost, for AI. For AIDC, so it actually comprises of 30% almost, of all your investment over in AIDC. But if you're using a cabling mechanism, it's not going to be efficient. It's not going to be efficient. So that's why you can see that a lot more in-cabinet cabling is happening, or in-server cabling is happening. But if you are doing this, the distance between the nodes will be very short. Hence, that's the reason why we see higher and higher density, over in AIDC. So that is basically, a key thing that we need to making sure that it's actually balanced, among these three: scale, how you build the scale, how you chop up the scale, and then how you build the network and linking them all together, and how you actually power them up, and making sure that it's reliable. Okay, so when we're talking about, when we are doing this, if we are having a supernode that comprises of hundreds of GPU, what it basically means is it's $1 billion of investment. So reliability becomes very, very important. So the TCO context, will no longer be, how do I go back? Okay. Will no longer be only a CAPEX and OPEX. So there's a lot of hidden incident that you will really need to take into consideration in advance. Incident that will be able to halt your operation will be able to actually let your your training or your inference non-functioning over minutes, over hours. And because all these possible potential incident will actually incur a lot losses to AIDC investment. So instead of direct loss and indirect loss, all these hidden loss is actually something we have to actually take into consideration. But because of the investment over in the L2 computing capability and hardware over in AIDC, so we can actually see that a safety operation investment is now is only 3% of the total investment over in the industry. So we actually urge DC operator to really making sure that you are investing enough in order to making sure the safe operation and also reliable operation of your AIDC. So to Huawei, when we are coming to how we see the data center is actually accelerating, especially over in our region in Asia, right? So we can actually see that there are actually 3 key factors in order to making sure an operator or a tenant will be able to achieve key business success. So the first is actually fast delivery. We used to be in the era where deploying a data center in 18 to 24 months or even longer than that. But today, like what we have actually been see over in ASEAN, in Southeast Asia, especially in Johor, data centers are deployed over in 14 months or even 10 months. So this is exactly what is actually taking place over in the industry today. So if you are actually deploying a data center that's more than 18 months, you are actually totally out of the competition in the market. Okay, and then elastic deployment. What do I mean elastic deployment? As what I said just now, we actually seen chipset is actually updating almost every year. But when we build a facility, we are actually building a facility by designing it, to be there for 10 to 15 years. So over in the 10 to 15 years, when there's actually a new chipset actually coming out that will require your building, your facility to adapt to it, how fast and how elastic you will be able to respond to that. So that is actually something very important for us to, to take into consideration, because the chipset performance, the power consumption, requirement, etc., always surprise us, right? They always surprise us in terms of what we need to do in for our facilities, to adapt to them. And then thirdly, of course, how do we making sure that we can continuously improving our TCO. This improvement doesn't mean major upgrade or major change of the total cost. Because of the huge investment and the huge power consumption over in the AIDC, a minor or a trivial improvement could actually save you millions of dollars, right? For example, a reduction of 0.1 PUE could actually save you 50 million, US dollar, compared, to in a gigawatt campus. So these are actually key things where we see, important factors, for AIDC business to be successful, especially over in Asia now. So in responding to that, leveraging on Huawei, experience over in the market, we will actually, we want to share today with you, we have come out with 3 guidelines, for constructing a AIDC. So the first is actually reliable. Like what I say, it has to be ultra reliable, because you are actually not only continue to operate, a AIDC that actually has billions of investment, you are actually also wanting to making sure that all your training will not be interrupted. So a 1 microsecond interruption of a training process will actually cost you 12 days in order to reconfigure and restart again. So that's basically the cost, that we are seeing over, the continuity, of the operation over in the AIDC is very important. Second is agile, right? So when you have new requirements, like some of the speakers actually shared before, we have so diversified requirements now, demand from different tenants, right? Whether from the west or from the east, and from different AI application, whether it's training or whether it's inference. So how can your AIDC, structure facility be able and be agile, to adapt to that? And then thirdly, of course, sustainable. You have to making sure that your investment is sustainable, the power energy is sustainable over in your design. So for Huawei, we pay a lot of attention, focus in our product and equipment. So I would like to introduce to you all, our market, industry leading, a modular UPS. So we can actually, live up to, 6 9, reliability, for whether it's module, cabinet, our system level, reliability with a high efficiency, from all our system, and of course high density. So one, because of a high density of modular, our module in our UPS, we will be able to assemble, a very high density, UPS, up to 800 kilowatt. So this is actually one of the highest actually over in the industry with very high efficiency. So I want to share you a video, on our UPS. Right. From UPS next, I would like to introduce to you Huawei Smart Li, lithium battery. So we actually heard a lot and read a lot, about lithium battery incident over in the world. But with the density of the AIDC that we are actually witnessing today, there's no other technology other than lithium battery that is most suitable, for our DC operation. So the key thing is not about what is how do we actually making sure that all this is being actually managed carefully, and so that we will be able to deploy lithium battery over in a larger scale over in our industry. So over in here, Huawei, what we have actually done is we have actually dedicated a lot of effort, and also research, and over in the past 3 years we actually spent more than 30 million Chinese yuan over in testing and also communicating with the global lithium safety institutes, as well as the firefighting authorities in different countries, like for example the National Fire Safety Institute over in China, Bomber over in Malaysia, and also the Central Fire Station over in Singapore, to exchange views and also learn about both everyone's best practices. So what we can actually conclude, actually from all this discussion and actually testings, is that the best way of making sure that a power is actually, lithium is being deployed safely over in the AIDC, is making sure that it's isolated. So Huawei recommendation is actually, to do a remote deployment, that to put your lithium battery outside of your IT hall. That will be the safest. But when you're pulling it outside of your IT hall, then the distance become an issue. So the cable cost will become another issue. And then hence, because of that, we actually built into our battery rack a voltage boosting capability to help you to save, power, the cable cost that you actually need, to link it up, from IT hall, to external battery bank. Okay, and this is also something very unique over in Huawei. And then our actually experiment, and discussions with many of the authorities and also safety, institutes has also gained us a lot of insights in giving, and providing guidances, to our customers as of how do you actually build your battery room. Okay, what are the safety features that you need to equip into your battery rooms. So with that, we are going to actually, launch, a white paper together with ITU to share all these experiences and also insights, within the industry. So I will have another teaser that I will share more with you, later on. All right, as well you can see, like we deploy a lot of AI detection mechanism into making sure that we'll be able to pre-detect, many of the hidden signal that will eventually may lead to an incident, for the battery. So the next product that I would like to introduce to you, is actually Huawei, power port solution. Okay, so this solution is actually a containerized, a power system plus a battery system over in a container. So and a highly reliable container. So over in the container, we will have a UPS, power cabinet, battery, cooling system, air conditioner, etc. So this system is actually a power system in one container that will be able to help our customers to do fast delivery. So like for example, to reduce, a delivery from 28 weeks, to 18 weeks, and then we'll be able to flexible expand according to your needs, because this containerized solution will be able to customize and reconfigure into the megawatt that you need actually for each of your deployment. And then it's a highly reliable because everything is actually pre-manufactured, pre-commissioned, and tested over in our factory before we ship to the site. So there's no on-site integration of all the cabinets, cabling, and etc. So this is actually a very important product for us to answer to the market, especially over in Southeast Asia. So I have another teaser that will explain more and will show you a lot more in terms of power port. So and then one thing that I also want to actually highlight is besides the capability, the higher reliability, the density that we're offering, we're also making sure that each of these containerized solutions are being conducted with simulation, CFD simulation, before it actually exits our factory. So we will be actually monitoring, the whole entropy, of within the circulation within the container, to making sure that everything will be actually living up to the design. Okay, I will show you another teaser. All right. So besides product, system, and solution, so the other thing that I would like to highlight over here is very important to also couple all these together, with services, to making sure that the running operation of the AI, DC is actually fully reliable. So in terms of services, what Huawei is providing, is a full life cycle, including inspection services and also reconstruction, services if you actually need to enhance your facility, to adapt to some of the changes over in the industry. And then in terms of, and then besides, services, design is very important. So what we have also making it easier for our customers is based on our RAS, recommendation guideline that I actually mentioned just now, reliable, agile, and safety. We have come up with 2021 standard reference design where our customer can quickly refer to, to start, your design or to actually have a conceptual, idea of how your AIDC will be like, and then with that, you'll be able to continue to enhance that, with your own consultants and your design house. And with this, what we can actually, introduce to you, not only on a product level, so it's actually, from a solution to a system level, in order to making sure that Huawei will be able to contribute to a fast delivery over at the site, and our solution will be able to optimize your TCO over in short, whether it's actually a mid-term or a long-term, and also making sure that you actually enjoy a full domain reliability and safety over in your data center, and also flexible evolution in order to meet your chipset and also your business needs. So. And then with that, I actually want to share with you one case study that we deployed over in Johor. This is a very high power density data center, AI data center with 124 kilowatt per rack, and then large scale, really large scale, AIDC, and with only and deliver only in 10 months time. Okay. Okay, my last slide, I would like to take my last slide, to introduce a little bit to you on Huawei R&D. All right, so I think it's very well known that Huawei is an R&D powerhouse. So, but when it comes to critical power, what we are investing is not only in our product and solution. So in general, we are investing 1 billion renminbi, Chinese yen every year, and then to come out with very innovative product. But on top of that, we are also having a lot of strategic investment over in material engineering and also in thermal management, and as well as a cooling algorithm. That is going to continue helping us, to meet the demand of our operators, whom actually are facing with a lot of unexpected and unforeseen, development over in our AI, industrial, revolution. So with that, I thank you, for your time and attention, and welcome, and to engage with us and drop us a question, after this, then we are happy to actually, answer whatever question that you might have on mind. Thank you very much, and I wish you a very good, event. Thank you.
Thank you very much for this presentation. If you want to talk further with Huawei Info, you can find them at stand 24. This is the end of our Tech Showcase presentations for today. We do have content running still on our main stage. We've got a panel that's about to start. So please join us there. But otherwise, thank you very much for joining us at DCD Connect Asia Pacific and on this showcase stage. It's been a pleasure to have you today. Thank you.
When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool. When the promise of AI surrounds us, our end-to-end solutions and services for AI-critical infrastructure configure at speed, scale, and deliver at volume. The world depends on data we power and cool.